Venus is our sister planet. She's literally, at some times during the year, the closest thing to Earth other than our natural satellite, the Moon. And so she has a story to tell us of almost another Earth, but different. And that divergent story of how she has such a massive atmosphere and our planet is such a perfect place for people is one we want to understand and tell.
For decades, astronomers imagined Venus as a humid tropical twin to Earth. But the first Soviet probes sent to investigate were instantly crushed by an atmosphere 90 times denser than our own. When engineers finally built a lander capable of surviving the descent, they expected to find a world locked in perpetual darkness. Yet the grainy photographs that beamed back revealed a landscape bathed in eerie light and scattered with anomalies that defy geological explanation. From the terrifying pressure that snapped spacecraft like twigs to the unexplained, shifting shapes captured in the Venera 13 panoramas, we are revisiting the only surface images ever taken to investigate why the evidence suggests our understanding of this hellish planet is fundamentally flawed. For centuries, Venus was a deception. Through the lens of a telescope, it appeared as a pristine, featureless sphere, shrouded in a thick blanket of white clouds that reflected the sun with a brilliance unmatched by any other star or planet. This opacity fueled human imagination. Because the surface was hidden, scientists and science fiction writers alike were free to project their own Earth-centric biases onto the world next door. In the early 20th century, the prevailing theory was that the clouds were made of water vapour. This led to the assumption that the surface was a wet tropical swamp, perhaps teeming with prehistoric life, protected from the sun by a perpetual overcast sky. It was the twin of Earth, just a little warmer and a little younger. The reality of Venus, however, is the most hostile environment in the solar system. It is a world where the greenhouse effect has run away completely, creating a surface temperature of 475 degrees Celsius. This is hot enough to melt lead, zinc, and tin. The atmosphere is not a protective blanket but a crushing weight of carbon dioxide, exerting a surface pressure of 90 atmospheres. Standing on the surface of Venus would feel like being submerged a kilometre deep in Earth's oceans, while simultaneously being roasted in an oven. The clouds are not water, but concentrated sulfuric acid. Exploring this world required a complete recalibration of what was technologically possible. Between 1961 and 1985, humanity launched a barrage of robotic emissaries to penetrate this veil. While NASA focused its primary efforts on the Moon and Mars, the Soviet Union claimed Venus. Their program, known as Venera, became one of the greatest engineering sagas in history. It was a sequence of missions defined by trial, catastrophic failure, and eventual hard-won success. The ultimate prize of this program was not just to land, but to see. The drive to place a camera on the surface and transmit a photograph back to Earth became a singular obsession, a way to strip away the centuries of speculation and confront the true face of our planetary neighbour. To conquer Venus, engineers had to discard the delicate spindly designs used for the Moon and Mars. They had to think in terms of bathyscaphs, deep-sea submersibles built to withstand the crushing abyss. The Soviet engineers at the Lavochkin Association, the bureau responsible for the Venera probes, essentially had to build a tank, fill it with delicate electronics, and then throw it into a volcano. The early failures were instructive. Venera 4, launched in 1967, was a martyr to science. It entered the atmosphere and deployed its parachute, expecting a pressure of perhaps 20 atmospheres. As it descended, transmitting data on temperature and pressure, the readings began to spike violently. The probe was designed to withstand 18 atmospheres. The reality was nearly 5 times that. At an altitude of 27 kilometers, the hull buckled and imploded. It was a silent, violent death, but the data it streamed during its dying moments rewrote the textbooks. The atmosphere was not just heavy, it was a supercritical fluid, behaving less like a gas and more like a liquid ocean of carbon dioxide. Armed with this terrifying new baseline, the Soviets abandoned the idea of a gentle descent. For Venera 7, launched in 1970, the parachute was redesigned to fail. The logic was ruthless. The longer the probe spent drifting down through the acid clouds, the more heat it absorbed. Speed was survival. The capsule was built as a titanium sphere, a coffin for instruments, capable of withstanding 180 atmospheres. It plummeted through the clouds, the parachute reefing to speed the descent, before finally deploying fully near the surface. The landing was hard, essentially a controlled crash, and the probe rolled onto its side. But the signal continued. For 23 minutes, a weak, fluctuating transmission beamed back to Earth. It was the first time humanity received a signal from the surface of another planet. The temperature was 475 degrees Celsius. The pressure was 90 bars. The probe died not from impact, but from heat stroke, cooked from the inside out. However, the Holy Grail remained elusive, a photograph. The challenge of placing a camera on Venus was optical as well as thermal. How do you keep a lens from melting? How do you keep the pressure from shattering the glass? Before we dive into this cosmic puzzle, let's take a moment to appreciate the scale of it all. This story is travelling across the globe, reaching you right now. I'm always curious to see our small planet mapped out in the comments, so let me know which part of the world you're joining this exploration from. And if you believe these cosmic stories are worth exploring, the best way to support our mission is by liking this video and subscribing for the next one. The engineers devised a system where the camera itself remained safely inside the cooled, pressurized titanium sphere. It would look through a specialized periscope made of quartz and diamond-coated glass, capable of withstanding the acid and the heat. The breakthrough came in October 1975 with Venera 9 and 10. These landers were massive 5-ton beasts. To keep the electronics alive long enough to transmit an image, they employed a unique phase-change cooling system. The interior was lined with packets of lithium nitrate trihydrate, a salt that melts at a specific temperature. As the interior heated up, the melting salt absorbed the thermal energy, keeping the electronics at a manageable operating temperature for nearly an hour. When Venera 9 landed, it jettisoned its lens caps, a complex pyrotechnic procedure in itself, and the scanner began to move. The image that slowly built up line by line on screens in Moscow was shocking. Scientists had expected a dark, dusty, smooth desert, eroded by the dense atmosphere. Instead, they saw a sharp, angular landscape. The ground was littered with flat, uneroded rocks scattered like broken pavement. The shadows were distinct. This proved that despite the thick clouds, sunlight did penetrate to the surface, diffusing into a perpetual gloomy twilight similar to a rainy day in London. The air was so clear that the horizon was visible, defying the expectation of a murky, dust-choked soup. Venera 13 and 14, landing in 1982, brought the surface into colour. The images revealed a world bathed in an eerie orange glow. The thick atmosphere filtered out all blue light, leaving only the red and orange spectrum to reach the ground. If you were standing there, the rocks would look dark grey, but under the Venusian sky, everything was sepia-toned. These probes also carried microphones. For the first time, we heard the sound of another world. It was not a howling gale, but a low, steady whisper of wind, occasionally punctuated by the sharp crack of the lander's metal, expanding and contracting in the thermal shock. However, Venera 14 also provided a moment of tragic comedy that highlighted the extreme difficulty of remote operations. The lander was equipped with a spring-loaded arm designed to smash into the ground and measure the compressibility of the soil. When the camera lens cap was ejected, it popped off and landed directly under the compressibility tester arm. When the arm deployed, it didn't measure the soil of Venus, it measured the compressibility of the lens cap brought from Earth. Even billions of kilometers away, Murphy's Law remained a universal constant. Despite these triumphs, the landers could only survive for a maximum of 2 hours. To understand the planet as a system, we needed to see through the clouds globally. This ushered in the era of radar mapping. The US Magellan mission in the early 1990s stripped Venus naked, digitally speaking. Using synthetic aperture radar, Magellan peered through the clouds to map 98% of the surface. The global map revealed a geology that was deeply unsettling to terrestrial geologists. Earth is defined by plate tectonics, a mosaic of moving crustal plates that recycle the surface, creating mountains, trenches, and earthquakes. Venus showed no sign of this. There were no mid-ocean ridges, no subduction zones. Instead, the planet appeared to be a stagnant lid world. The heat from the core, unable to escape through the constant motion of plates, builds up until the entire crust becomes unstable. The cratering record tells a violent story. On Earth and the Moon, craters of all ages are found, allowing us to date different regions. On Venus, the craters are randomly distributed and remarkably pristine. There are almost no degraded ancient craters. This suggests that the entire surface of Venus is roughly the same age, somewhere between 300 and 600 million years old. The leading hypothesis is the catastrophic resurfacing event. It posits that roughly 500 million years ago, the stress on the crust became too great. The entire planet underwent a massive volcanic convulsion. The crust effectively melted or was buried under kilometers of lava in a geological blink of an eye, erasing all past history. Venus is a planet that hits the reset button, wiping its own memory clean in global paroxysms of fire. The chemical analysis of the surface rocks by the Venera landers, combined with Magellan's radar data, confirmed a surface dominated by tholeiitic basalt, similar to the volcanic rocks of Earth's ocean floors. But there are anomalies. The pancake domes, steep flat-topped volcanoes, suggest lava that was incredibly viscous, perhaps rich in silica, oozing out like toothpaste under the immense atmospheric pressure. Then there are the tesserae, highly deformed elevated terrains that look like crumbled aluminum foil. These may be the only surviving remnants of the ancient continents, the ghosts of the Venus that existed before the last global cataclysm. The exploration of Venus also forces us to confront the fragility of planetary habitability. Isotopic ratios of hydrogen and deuterium in the upper atmosphere suggest that Venus once had water, perhaps a global ocean's worth. In its youth, Venus may have been the first habitable world in the solar system, a blue marble long before Earth cooled. But as the sun brightened, the oceans evaporated. Water vapor is a potent greenhouse gas. This triggered a feedback loop. More heat, more evaporation, more heat. Eventually, the oceans boiled off entirely. Solar radiation broke the water molecules apart. The hydrogen escaped to space, and the oxygen bonded with the carbon and surface rocks. The plate tectonics stopped because water acts as a lubricant for crustal movement. Without it, the machine seized up. The carbon dioxide, usually scrubbed from the atmosphere by rain and rock weathering on Earth, had nowhere to go. It accumulated, building the crushing atmosphere we see today. Venus, therefore, is not just a planet. It is a laboratory of the apocalypse. It is the end state of a biosphere gone wrong. It demonstrates that the difference between a garden and an oven is merely a matter of atmospheric chemistry and distance from the star. After the collapse of the Soviet Union, the silence returned. The intense heat and pressure meant that Venus exploration was expensive and high risk, offering short mission durations compared to the years-long rovers on Mars. For decades, Venus was the forgotten sibling, bypassed by probes heading to the outer solar system. But recently, the scientific eye has turned back. The controversial detection of phosphine, a potential biomarker, in the upper temperate cloud decks has reignited the debate about life, not on the hellish surface, but in the skies. At an altitude of 50 kilometers, the pressure is 1 atmosphere and the temperature is a manageable 20 to 30 degrees Celsius. It is the most Earth-like environment in the solar system, aside from the acid droplets. Could microbial life, survivors from the ancient oceans, have migrated to the clouds, living in eternal suspension? This question, along with the need to understand the planet's divergence from Earth, has spurred a new generation of missions. NASA's Da Vinci and Veritas, along with ESA's Envision, are preparing to return. Da Vinci will drop a probe through the atmosphere, tasting the air with modern spectrometers to finally resolve the history of water. Veritas and Envision will map the surface with new, high-resolution radar, looking for active volcanism, the beating heart of the planet. The legacy of the Venera program stands as a testament to brute force engineering and the audacity of the human spirit. Those titanium spheres, now slowly corroding on the basaltic plains of Sedna Planitia and Phoebe Regio, are monuments to the first time humanity touched hell and lived to tell the tale. They remind us that the universe is not tailored for our comfort. To know it, we must build machines that can endure what we cannot, acting as our proxies in the fire. Venus waits, a shrouded warning and a geological treasure trove, demanding that we return not just to look, but to understand the delicate balance that sustains life on our own pale blue dot. The Soviet Union's fixation on Venus was driven by a complex mixture of scientific curiosity and Cold War geopolitics. In the race for space dominance, The United States had secured the first successful flyby of Mars and was rapidly moving toward a manned lunar landing. The Soviet leadership needed a victory that was distinct and unchallenged. Venus, with its proximity and mystery, offered a target that was technically demanding yet reachable. The Venera program was established not merely to fly past the planet, but to touch it. The goal was to place a sovereign emblem on the surface and transmit data from the ground, a feat that would demonstrate the superiority of Soviet materials science and radio engineering. Behind this ambition sat a cadre of brilliant designers and engineers at the Lavochkin Association, the bureau responsible for the design of Soviet planetary probes. They were operating in an environment of intense pressure and secrecy. Resources were vast but not infinite, and the political leadership demanded tangible results. The scientific objectives were clear: determine the composition of the atmosphere, measure the temperature and pressure, and map the surface. However, the engineering reality was that they were designing machines for a world they did not understand. Every mission was a hypothesis tested against an unknown variable, and the cost of an incorrect hypothesis was the total destruction of the spacecraft. The initial phase of the Venera program was characterized by a painful process of trial and error, a groping in the dark against a planetary adversary that refused to conform to terrestrial expectations. Between 1961 and 1965, the Soviet Union launched a series of probes that failed to leave Earth orbit, lost communication en route, or missed the planet entirely. These failures were not merely technical glitches, they were symptoms of the immense difficulty of interplanetary navigation in the dawn of the space age. However, the relentless pace of the Soviet industrial machine meant that for every failure, a replacement was already on the production line. The engineering philosophy was iterative: launch, fail, learn, fix, and launch again. The turning point came with Venera 4 in 1967. This mission was designed based on the prevailing scientific consensus of the time, which estimated the surface pressure of Venus to be perhaps 10 to 20 times that of Earth. The probe was built like a diving bell, robust but optimistic. As it descended into the Venusian clouds, it deployed its parachute and began transmitting data. The results were shocking. The thermometer and barometer readings spiked almost immediately. The atmosphere was not merely dense, it was a crushing ocean of supercritical carbon dioxide. Venera 4 never reached the surface. At an altitude of roughly 26 kilometers, the external pressure exceeded the hull's structural limit of 22 atmospheres. The probe imploded, crushed like a tin can, its final transmission a scream of data that rewrote the textbook on Venusian physics. This failure was, in fact, a magnificent scientific triumph. It provided the Lavochkin engineers with the hard numbers they needed. They realized that their previous designs were woefully inadequate. To touch the surface, they would not be building a spacecraft in the traditional sense. They needed to build a bathyscaphe capable of withstanding pressures found a kilometer beneath the Earth's oceans, while simultaneously resisting temperatures high enough to melt lead. The redesign was radical. For the subsequent missions, the scientific payload was reduced to accommodate a massive increase in structural armor. The descent module was forged as a single spherical shell of titanium, the strongest shape known to engineering. To survive the descent, the parachute strategy was altered. A large parachute would mean a slow descent, cooking the electronics before they reached the ground. The new strategy was a controlled crash. The parachute would deploy to slow the initial entry, but then be cut loose or reefed, allowing the probe to freefall rapidly through the oven-like atmosphere, relying on a rigid aerodynamic brake, a metal drag ring, to slow it just enough to survive the impact. Venera 7, launched in August 1970, was the embodiment of this brute force engineering. It was a tank thrown into the sky. Upon arrival, the parachute partially failed, and the probe hit the surface at a speed of roughly 17 meters per second, harder than intended. The telemetry signal vanished, and mission control feared another failure. However, post-processing of the radio signals revealed a faint, steady pulse. Venera 7 had survived. For 23 minutes, it transmitted from the surface of Venus. It was the first time in human history that a signal had been received from the surface of another planet. The data confirmed a surface temperature of 475 degrees Celsius and a pressure of 90 atmospheres. The Soviet Union had effectively landed on Hell. With the survival problem theoretically solved, the ambition shifted from mere existence to observation. The Soviet leadership wanted a photograph. This presented a nightmare of optical engineering. How does one place a camera lens on the surface of Venus without the glass melting or cracking under the thermal shock? The solution devised for the Venera 9 and 10 landers, launched in 1975, was ingenious. The cameras were not placed outside. Instead, they were housed deep inside the cooled, pressurized titanium sphere. They looked out through a complex periscope system made of quartz and diamond-coated glass, designed to withstand the acid and heat. To keep the interior cool long enough to transmit images, the engineers utilized a phase-change cooling system. The lander's interior was lined with packets of lithium nitrate trihydrate, a salt that melts at a specific temperature. As the heat from the Venusian environment penetrated the hull, it was absorbed by the melting salt, keeping the electronics at a stable operating temperature for roughly an hour. This was the thermal lifetime of the lander. Once the salt was fully melted, the internal temperature would skyrocket and the probe would die. On October 26, 1975, Venera 9 touched down and blew off its lens caps. The image that slowly built up on the screens in Moscow was mesmerizing. Scientists had expected a dark, murky landscape, obscured by the thick clouds. Instead, they saw a sharp, clear image of a rocky plain. The rocks were flat and angular, not eroded by wind or water, suggesting a relatively young geological surface. The lighting was diffuse, similar to a cloudy day on Earth, casting no sharp shadows. It was a stark alien desolation, terrifying in its stillness. The program reached its zenith in the early 1980s with Venera 13 and 14. These 5-ton behemoths were launched on the Heavy Proton rocket, allowing for even more sophisticated instrumentation. They carried color cameras, drills to sample the soil, and microphones. The color images revealed a world bathed in an eerie orange light. The thick atmosphere filtered out all blue wavelengths, meaning that if a human stood there, the sky would be an oppressive, glowing apricot dome. The soil analysis, performed by a drill that had to operate in 475-degree heat, identified the ground as tholitic basalt, similar to the volcanic rock found on Earth's ocean floors. Venera 13 also returned the first audio recording from another world. It captured the sound of the Venusian wind, a low, steady drone, punctuated by the sharp metallic crack of the lander's pyrotechnic charges firing. This was the sound of a planet that had been silent for hundreds of millions of years, briefly interrupted by the noise of human machinery. However, the program was not without its moments of grim irony, illustrating the unforgiving nature of remote exploration. On Venera 14th, the mission plan called for a spring-loaded arm to swing out and smash a probe into the ground to measure the soil's compressibility. At the same time, the camera lens cap was ejected to clear the view. In a twist of fate that defies probability, the lens cap popped off, landed on the ground, and rolled directly to the spot where the compressibility arm was programmed to strike. When the arm deployed, it slammed into the lens cap. The telemetry sent back data indicating the surface of Venus was exactly as hard as a titanium lens cap. Even across millions of kilometers, mechanical bad luck could still strike. The final act of the Soviet Venus exploration was the Vega program in 1985. By this time, the focus had shifted to understanding the dynamics of the atmosphere. The Vega missions deployed balloons, aerobots, that floated in the upper atmosphere, roughly 54 kilometers above the surface. At this altitude, the temperature and pressure were Earth-like. The balloons drifted for days, tracked by a global network of radio telescopes, revealing that the upper atmosphere super-rotates, whipping around the planet much faster than the planet itself spins. This was a triumph of international cooperation during the waning days of the Cold War, with French and American scientists assisting in tracking the Soviet probes. The collapse of the Soviet Union in 1991 brought an abrupt end to this era of exploration. The blueprints for more advanced landers, capable of roving the surface or surviving for days rather than minutes, were shelved. The Lavochkin Association had achieved what no other nation had attempted: a comprehensive invasion of the solar system's most hostile environment. They had launched over 24 missions, littered the surface with titanium carcasses, and peered beneath the veil. Today, the Venera landers sit silently on the surface of Venus. The intense heat and acidic atmosphere would have long since stripped away their paint and corroded their external sensors. The parachutes have likely disintegrated into dust, but the pressure vessels, the titanium hearts of the machines, likely remain intact. They are monuments to a specific moment in human history when the drive to know the unknown outweighed the fear of failure. They stand as the only human artifacts on a world that serves as a cautionary tale of planetary evolution, a greenhouse effect run amok, a twin sister that grew up to be a monster. The data they returned remains the bedrock of our understanding of Venus, a legacy of hard-won knowledge etched in the brief high-pressure bursts of radio waves sent before the silence returned. The Soviet Venus program proved that with enough armor, enough thrust, and enough persistence, humanity could endure, however briefly, in the fires of a planetary hell. The early history of the Venera program is a catalogue of crushed metal and silence. The first few attempts were plagued by launch vehicle failures and radio malfunctions, but as the Soviets began to reach the planet, the atmosphere itself became the enemy. In 1967, Venera 4 arrived at Venus with a design based on the wet swamp model. The engineers believed the pressure would be roughly 20 times that of Earth. The probe entered the atmosphere and deployed its parachute, expecting a slow, controlled drift to the ground. It never made it. The telemetry ceased at an altitude of 27 kilometers. The probe had not burned up, it had been crushed. The atmospheric pressure at that altitude already exceeded the hull's structural limit, and it was nowhere near the surface. This failure forced a terrifying realization. The atmosphere was far denser than anyone had predicted. The engineers had a limited window before the next launch opportunity in 1969, so they attempted a stopgap solution for Venera 5 and Venera 6. Unable to redesign the pressure vessel in time, they reduced the size of the parachutes. The logic was that a faster descent would get the probe through the upper atmosphere more quickly, potentially allowing it to reach the surface before the heat and pressure destroyed it. The plan failed. Both probes imploded roughly 11 kilometers above the ground. These missions were not wasted, however. They provided the crucial data points needed to understand the true scale of the Venusian atmosphere. It was now clear that to survive landing, a spacecraft could not be built like an airplane. It had to be built like a bathyscarf. The realization that Venus was less a tropical swamp and more a planetary pressure cooker marked a pivotal shift in Soviet engineering philosophy. The era of the aerospace probe was over. The era of the interplanetary submarine had begun. The Lavochkin Association, under the brilliant guidance of chief designer Georgy Babakin, scrapped the previous blueprints. For the upcoming 1970s launch window, they designed Venera 7 with a singular, brutal objective: survival. The new descent module was a fortress. The delicate aluminum alloys were replaced with a forged titanium shell, machined to absolute spherical perfection to distribute the crushing external load evenly. The engineers modelled the hull to withstand 180 atmospheres of pressure, double the revised estimates, and temperatures of 540 degrees Celsius. This over-engineering came at a cost. The mass of the scientific payload had to be slashed to accommodate the armour. There would be no cameras, no complex soil analyzers. Venera 7 was effectively a hardened thermometer and barometer thrown into a volcano. To further ensure survival, the parachute system was radically altered. A large parachute meant a slow descent, which meant a longer exposure to the roasting atmosphere. The new plan was a reef and release strategy. The parachute would open to slow the probe through the upper clouds, then be partially constricted to speed up the fall, minimizing the heat soak. When Venera 7 arrived at Venus in December 1970, the stakes were absolute. As the probe plunged into the night side of the planet, the parachute reefing mechanism failed. The chute melted or tore away earlier than intended, and the titanium sphere plummeted in freefall for the final leg of the journey. It struck the surface at a speed of roughly 17 meters per second, hard enough to crack concrete. The telemetry signal vanished instantly. In mission control, the silence was interpreted as yet another failure, another expensive crater on an alien world. However, weeks later, during a review of the raw radio astronomer tapes, a faint, steady signal was discovered hidden in the background noise. Venera 7 had survived. It had toppled over on impact, aiming its antenna away from Earth, but it was alive. For 23 minutes, it whispered the secrets of the surface: 475 degrees Celsius, 90 atmospheres. It was the first human artifact to transmit data from the surface of another planet, confirming once and for all that Venus was a hellscape. With the survival problem theoretically solved, the Soviet ambitions expanded. Venera 8, launched in 1972, repeated the success but landed on the day side. Its crucial mission was to measure light levels. If the thick clouds blocked the sun entirely, sending a camera on future missions would be pointless. Venera 8 confirmed that surface illumination was comparable to a gloomy, overcast day on Earth, dim but sufficient for photography. This greenlit the most ambitious phase of the program, the heavy landers. The shift to the powerful Proton rocket allowed for a new generation of spacecraft. Venera 9 and 10, launched in 1975, were 5-ton behemoths. These were not simple spheres, they were complex laboratories encased in thermal armour. To keep the electronics functioning long enough to take a picture, the engineers developed a phase-change cooling system. The interior was lined with packets of lithium nitrate trihydrate, a salt that melts at a specific temperature. As the probe heated up, the melting salt absorbed the thermal energy, maintaining the interior at a balmy operational temperature for nearly an hour. The cameras themselves were not exposed to the outside. They remained safely inside the pressure hull, looking through periscopes made of quartz and diamond-coated glass designed to resist the acid and heat. On October 27, 1975, Venera 9 touched down. The shock absorbers groaned. The lens caps were blown off by pyrotechnic charges, and the Cyclopean eye began to scan. The image that slowly built up on the screens in Moscow shattered the remaining illusions about Venus. Geologists had predicted a smooth, eroded desert, worn down by the thick atmosphere. Instead, Venera 9 revealed a landscape of sharp, angular rocks. The ground was littered with flat, uneroded stones, suggesting a geologically young surface that had not been subjected to wind or water erosion for eons. The shadows were diffuse, there was no dust in the air, and the horizon was clearly visible. It was a stark, rocky desolation, terrifyingly still. The zenith of the program arrived in the early 1980s with Venera 13 and 14. These missions were designed to capture the world in colour and to perform the audacious feat of drilling into the surface. The engineering required to drill into rock at 475 degrees Celsius, in a pressure environment that would crush a nuclear submarine, is difficult to overstate. The lubrication oils used in standard machinery would instantly vaporize or combust on Venus. The engineers had to develop entirely new dry lubricants based on molybdenum disulfide and construct the drill mechanisms with thermal expansion tolerances calculated to the micrometer. If the metal expanded too much in the heat, the drill would seize too little, and it would shatter. Venera 13 landed on March 1, 1982. It survived for 127 minutes, far exceeding its design life. The colour images it returned showed a world bathed in an eerie, sickly orange light. The thick atmosphere filtered out all blue wavelengths, meaning the sky was a heavy, glowing apricot dome. The rocks, which would appear grey on Earth, took on a sepia tone. The probe drilled into the surface, sucked a sample into a vacuum airlock, and analysed it with an X-ray fluorescent spectrometer. The verdict: tholigitic basalt, a volcanic rock similar to that found on Earth's mid-ocean ridges. Venus was a volcanic planet. However, the program was not without its moments of dark comedy, illustrating the capricious nature of space exploration. Venera 14, landing 4 days later, executed a perfect touchdown. The mission plan called for a spring-loaded arm to swing out and strike the ground to measure the compressibility of the soil. Simultaneously, the camera lens cap was ejected to clear the view. In a twist of fate that defies probability, the lens cap popped off, caught the dense wind, and landed exactly where the compressibility arm was programmed to strike. When the arm slammed down, it did not measure the soil of Venus. It measured the compressibility of a Soviet titanium lens cap. The telemetry confirmed that the lens cap was, indeed, very hard. Even across millions of kilometers, human error and bad luck remained universal constants. These missions also carried microphones, capturing the first audio recordings from another world. They did not hear the roaring gales that fiction writers had imagined. Instead, they recorded a low, steady drone, the sound of a thick, viscous wind moving at low speed but with immense momentum. This silence was occasionally punctuated by the sharp, metallic crack of the lander's structure warping under the thermal stress, a lonely sound of a machine dying in the heat. The final chapter of the Soviet Venus saga was the Vega program in 1985, a hybrid mission that targeted both Venus and Halley's Comet. The Vega landers were accompanied by balloons, aerobots, that were deployed into the upper atmosphere. Floating at an altitude of 54 kilometers, where the temperature and pressure are remarkably Earth-like, these balloons drifted for days. tracked by a global network of radio telescopes. They revealed that while the surface is stagnant, the atmosphere is in a state of super-rotation, whipping around the planet at hundreds of kilometers per hour, driven by the solar energy absorbed by the dark UV absorbers in the clouds. By the time the Soviet Union collapsed, the Venera program had achieved the impossible. They had launched nearly 30 missions to the morning star. They had turned a point of light in the sky into a physical place, a world of orange skies, crushing pressure, and volcanic plains. The technological legacy of the Venera program remains unique. No other nation has attempted to land on the surface since. The complexity of the cooling systems, the pressure vessels, and the high-temperature electronics required to survive even an hour on Venus makes Mars exploration look comparatively simple. The silence that has fallen over Venus since 1985 is not due to a lack of interest, but a testament to the immense difficulty of the challenge. The sheer hostility of the environment means that standard electronics melt. Solar panels are useless on the surface due to the dim light and heat, and batteries have incredibly short lifespans. The Soviet engineers overcame this by accepting the transience of their machines. They built kamikaze robots, designed to live fast, gather data frantically, and die young. Looking back, the catalogue of crushed metal from the early days was the necessary price of admission. The wreckage of Venera 4, 5, and 6 lies crushed on the plains of Venus, flattened to the thickness of foil, indistinguishable from the rocks. But they paved the way for the titanium monuments of Venera 13 and 14, which likely still sit intact on the surface today. The heat would have long since fried their internals, the acid would have etched their optical glass, and the paint would have peeled away, but the titanium shells remain. They stand as silent sentinels in the gloom, the only evidence that life from the third planet once touched the surface of the second, stared into the fire, and managed to send a message home before burning up. The story of Venera is a reminder that the universe is not tailored for our survival. It is indifferent and violent, and understanding it requires a stubbornness that borders on the irrational, the very quality that defined the Soviet space program at its height. The design for Venera 7 marked a total departure from traditional aerospace engineering. To survive 90 atmospheres of pressure, the descent module was cast as a single, spherical titanium shell. This was a brute force approach to planetary exploration. Scientific instruments were stripped away to save weight for armour. There were no solar panels, only heavy internal batteries. There were no windows. The engineers were essentially building a cannonball designed to survive a descent into hell. But pressure was only half the problem. The heat was the true killer. Standard electronics fail instantly at 475 degrees Celsius. Insulation alone was insufficient because it only slows heat transfer. Eventually, the heat penetrates. The Soviet solution was to turn the lander into a temporary heat sink. Before separating from the orbiter, the system circulated supercooled fluid through the pressure vessel, bringing the internal temperature down to -10 degrees Celsius. The probe began its mission as a block of ice falling into a furnace. To handle the heat generated during the 50-minute descent, the interior was packed with lithium nitrate trihydrate. This chemical melts at 30 degrees Celsius, absorbing massive amounts of thermal energy in the process without rising in temperature. This phase change material bought the lander roughly an hour of life on the surface, before the system boiled over and died. The launch of Venera 7 in August 1970 was the first test of this interplanetary submarine philosophy. As the lander plunged into the night side of the planet, the engineering limitations of the era immediately made themselves known. The parachute, designed to reef and then fully deploy, partially failed during the descent. The polymer fabric, subjected to temperatures that would liquefy Teflon, likely melted or tore, causing the probe to fall faster than calculated. It struck the surface at a velocity of roughly 17 meters per second, a highway car crash impact. The telemetry signal vanished instantly, and for weeks the mission was classified as another failure in a long line of disappointments. However, a meticulous review of the radio tapes revealed a faint, ghostly signal hidden in the background noise. The probe had survived the impact but had toppled onto its side, misaligning its antenna. For 23 minutes it whispered the secrets of the surface. 475 degrees Celsius, 90 atmospheres. The ice block strategy had worked. Humanity had touched the surface of hell. With the survival problem theoretically solved, the ambition of the Lavochkin engineers expanded from mere existence to observation. Venera 8, launched in 1972, landed on the day side to answer a crucial question. Was there enough light to see? The thick cloud deck might have plunged the surface into eternal darkness, rendering cameras useless. The photometers on Venera 8 confirmed that surface illumination was comparable to a gloomy, overcast autumn day in Moscow, dim but sufficient for photography. This greenlit the next, most audacious phase of the program, the heavy landers. The shift to the powerful Proton rocket allowed for a new generation of spacecraft, beginning with Venera 9 and 10 in 1975. These were 5-ton behemoths, shedding the spherical simplicity of their predecessors for a more complex multi-component architecture. However, the core remained the spherical pressure vessel. To capture images, the engineers faced an optical nightmare. Placing a glass lens on the outside was impossible. The thermal shock would shatter it, or the pressure would deform it, ruining the focus. The solution was the telephotometer, a mechanical scanning camera housed deep inside the cooled, pressurized hull. It looked out through a thick periscope made of quartz and diamond-coated glass, engineered to resist the corrosive sulfuric acid and the immense pressure. On October 22, 1975, Venera 9 touched down on a slope of 20 degrees. The shock absorbers groaned under the weight, the pyrotechnic charges fired to blow off the lens caps, and the cyclopean eye began to scan. The image that slowly built up pixel by pixel, line by line on the screens in Moscow shattered the remaining illusions about Venus. Geologists had predicted a smooth, eroded desert, worn down by the thick atmosphere acting like a sandblaster over eons. Instead, Venera 9 revealed a landscape of sharp, angular rocks. The ground was littered with flat, uneroded stones, suggesting a geologically young surface that had not been subjected to significant wind or water erosion. The shadows were diffuse. There was no dust in the air, and the horizon was clearly visible. It was a stark, rocky desolation, terrifyingly still. The zenith of the program arrived in the early 1980s with Venera 13 and 14. These missions were designed to capture the world in colour and to perform the mechanical miracle of drilling into the surface. The engineering required to drill into rock at 475 degrees Celsius in a pressure environment that would crush a nuclear submarine is difficult to overstate. The lubrication oils used in standard machinery would instantly vaporize or combust on Venus. The engineers had to develop entirely new dry lubricants based on molybdenum disulfide and construct the drill mechanisms with thermal expansion tolerances calculated to the micrometer. If the metal expanded too much in the heat, the drill would seize. Too little, and it would shatter. Venera 13 landed on March 1, 1982. It survived for 127 minutes, far exceeding its design life of 32 minutes. The cooling system, a triumph of thermodynamic engineering, held back the inevitable heat death just long enough. The colour images it returned showed a world bathed in an eerie, sickly orange light. The thick atmosphere filtered out all blue wavelengths, acting as a massive blue blocking filter. This meant the sky was a heavy, glowing apricot dome. The rocks, which spectral analysis later confirmed were thallitic basalt similar to Earth's mid-ocean ridges, took on a sepia tone. The drill deployed, hummed against the rock, and successfully sucked a sample into a vacuum airlock for X-ray fluorescence analysis inside the hull. This confirmed Venus was a volcanic planet, likely resurfaced by massive lava flows within the last billion years. Simultaneously, the lander activated a microphone. For the first time, human ears heard the sound of another world. It was not the roaring gale fiction writers had imagined. The wind on the surface of Venus moved slowly, like a viscous current of water, due to the high density. The microphone recorded a low, steady drone, occasionally punctuated by the sharp, metallic crack of the lander's structure, warping under the thermal stress, the lonely sound of a machine dying in the heat. However, the program was not without its moments of grim irony, illustrating the unforgiving nature of remote exploration and the perverse influence of probability. Venera 14, landing 4 days later, executed a perfect touchdown. The mission plan called for a spring-loaded arm to swing out and strike the ground to measure the compressibility of the soil. Simultaneously, the camera lens cap was ejected to clear the view. In a twist of fate that defies statistics, the lens cap popped off, caught the dense wind, and landed exactly where the compressibility arm was programmed to strike. When the arm slammed down, It did not measure the soil of Venus, it measured the compressibility of a Soviet titanium lens cap. The telemetry confirmed that the lens cap was indeed very hard. Even across millions of kilometers, mechanical bad luck remained a universal constant. The final act of the Soviet Venus saga was the Vega program in 1985, a hybrid mission that targeted both Venus and Halley's Comet. The Vega landers were accompanied by a brilliant divergence in engineering strategy. The aerobots. Realizing the surface was a death trap, the Soviets deployed balloons into the upper atmosphere. Floating at an altitude of 54 kilometers, where the temperature and pressure are remarkably Earth-like, roughly 30 degrees Celsius and 1 atmosphere, these balloons drifted for days. Tracked by a global network of radio telescopes, a rare moment of Cold War cooperation involving NASA and the French Space Agency, the balloons revealed that the atmosphere was in a state of superrotation. While the solid planet rotates agonizingly slowly, one day on Venus is longer than its year, the atmosphere whips around the planet at hundreds of kilometers per hour. The balloons bobbed in turbulent winds, measuring vertical gusts that would have destroyed a terrestrial aircraft. This data suggested a planetary engine of immense power, driven by the solar energy absorbed by unknown UV-absorbing compounds in the clouds, compounds that some modern astrobiologists tentatively suggest could be signs of microbial life, though the Soviet engineers of the 80s were focused purely on fluid dynamics. The collapse of the Soviet Union in 1991 brought an abrupt end to this era of heavy metal exploration. The blueprints for more advanced landers, capable of roving via wind-driven wheels or surviving for days using seismic power, were shelved. The Lavochkin Association had achieved what no other nation had even attempted: a comprehensive invasion of the solar system's most hostile environment. They had launched over 24 missions, littered the surface with titanium carcasses, and peered beneath the veil. The engineering legacy of the Venera program is a masterclass in specific impulse innovation. They did not try to terraform the planet to suit the machine. They mutated the machine to suit the planet. They accepted the transience of their creation. In the West, spacecraft are built to last years: Voyager, Curiosity, Spirit. The Venera probes were kamikaze robots, designed to live fast, gather data frantically, and die young. They were disposable heroes. Today, those landers sit silently on the surface of Venus. The intense heat would have long since equalized, frying their internal electronics. The sulfuric acid rain, which evaporates before hitting the ground but exists as a mist, might have etched the optical glass. The paint would have peeled away within hours, but the pressure vessels, the titanium hearts of the machines, likely remain intact. Titanium is incredibly resistant to corrosion. They stand as silent sentinels in the gloom, the only evidence that life from the third planet once touched the surface of the second. Their existence poses a fascinating thought experiment for future archaeologists. If humanity were to disappear, and a future spacefaring species were to visit the solar system, the artifacts on the Moon and Mars would be easy to find. But the Venera probes are hidden. To find them, one must descend into the fire. Finding them would prove that the creators were not just explorers, but masters of material science. The crushed remains of Venera 4, 5, and 6 serve as warning buoys, while the upright skeletons of Venera 13 and 14 stand as monuments to the brute force era of discovery. The data they returned remains the bedrock of our understanding of Venus. Every climate model of global warming, every atmospheric simulation of exoplanets, relies on the ground truth data bought with the lives of these machines. They taught us that the greenhouse effect is not a theory, but a physical reality that can strangle a world. They showed us that a planet can be geologically alive but biologically dead. And they demonstrated that with enough armor, enough thrust, and enough persistence, engineering can overcome even the laws of hell, if only for 127 minutes. As we look toward future missions, NASA's Da Vinci Plus, ESA's Envision, we are returning to the playbook written by Lavochkin. The proposed landers look strikingly similar to their Soviet ancestors: spheres, phase change cooling, and rapid descent profiles. The physics of Venus has not changed, and thus the engineering solutions converge on the same singular truth. To survive Venus, you must become as hard as the planet itself. The torch has been passed, but the footprints, or rather the impact craters and landing rings of the Soviet giants remain, waiting in the crushing dark for the next visitor to arrive. Once the survival of the lander was theoretically possible, the ambition returned to photography. But placing a camera on Venus presented a unique optical paradox. A traditional television camera of the 1970s used a large, fragile cathode ray tube and required a glass lens. Putting a large glass window in the side of a pressure vessel, rated for 90 atmospheres, was structural suicide. The window would be the weak point that caused an implosion. Furthermore, the glass would likely crack or fog under the thermal stress. The solution was the telephotometer, a device that functioned more like a mechanical scanner than a camera. The imaging system remained safely buried deep inside the cooled titanium sphere. It looked out through a tiny cylindrical quartz window, thick enough to withstand the crushing pressure. A small mirror rotated back and forth behind this window, collecting light from a single point on the surface and directing it into a sensor. The sensor measured the brightness of that dot, transmitted the value, and then the mirror moved to the next dot. This process was agonizingly slow. It took many minutes to build a single panoramic image line by line. If the probe overheated before the scan was complete, the image would be cut off forever. The engineers were trading speed for durability, betting that a slow mechanical eye had a better chance of survival than a complex electronic one. The successful deployment of the telephotometer on Venera 9 in October 1975 marked the transition from blind survival to true exploration. However, before a single photon could be collected, the engineers had to answer a fundamental question that had plagued astronomers for decades. Was there any light to capture? The sheer density of the Venusian atmosphere, 90 times thicker than Earth's, led many to fear that the surface was plunged into a perpetual, abyssal night. If the clouds absorbed all solar radiation, the telephotometer would merely scan a pitch-black void, rendering the immense engineering effort futile. The answer had come 3 years earlier from Venera 8, a blind lander equipped with photometers. It confirmed that while the sun was never visible as a distinct disk, the thick atmosphere scattered the light, creating a diffuse illumination roughly equivalent to a cloudy autumn afternoon in Moscow. The stage was lit. The actors just had to arrive. When Venera 9 touched down, the immediate challenge was the pyrotechnic release of the lens caps. On a world where mechanical failure was the norm, this simple action was a critical point of failure. The landers were equipped with 2 cameras to provide a near 360-degree panoramic view. On Venera 9, one of the lens caps failed to release, a victim of the immense pressure jamming the mechanism or the heat warping the metal. The probe was half blind, but the remaining eye began its slow mechanical sweep. The data trickled back to Earth at a baud rate that would seem comically slow to the modern digital age, mere bits per second. In the control rooms of the Soviet Union, scientists huddled around thermal paper printouts and primitive monitors, watching the image build line by line. The anticipation was excruciating. They expected to see a smooth, sandy desert. The logic of the time dictated that an atmosphere this dense would act like a hyper-efficient sandblaster. Over millions of years, the wind and chemical weathering should have ground any geological features down to a fine, polished silt. Instead, the image that emerged was a shock to the geological community. Venera 9 revealed a landscape of sharp, angular rocks. The ground was a chaotic scree of flat, uneroded stones, casting distinct shadows. There was no sand dunes, no smoothed pebbles. The sharpness of the rocks implied a terrifying stillness. It suggested that despite the density of the atmosphere, the surface winds were relatively slow, lacking the energy to erode the hard rock significantly. More importantly, it implied that the surface was geologically young. These rocks had not been sitting there for billions of years. They were fresh, likely the result of recent volcanic fracturing or tectonic upheaval. The swamp theory was dead. The volcanic hellscape theory was born. The apex of this visual reconnaissance came 7 years later with Venera 13 and 14. These landers were the technological zenith of the Soviet planetary program. They were not just looking for shapes, they were looking for color. The engineers included color calibration charts on the lander's casing, strips of blue, green, red and white paint of known chemical composition. By comparing how these colors appeared on Venus to how they appeared in the lab, scientists could reconstruct the true spectrum of the alien light. The images from Venera 13 were breathtaking and deeply unsettling. They revealed a world bathed in a suffocating, sickly orange glow. The atmosphere of Venus acts as a massive blue blocking filter. the Rayleigh scattering that gives Earth its blue sky is overwhelmed by the sheer volume of gas and the sulfur in the clouds. Blue light is scattered and absorbed long before it hits the ground, leaving only the red, orange, and yellow wavelengths to illuminate the surface. If a human were to stand on Venus, looking through the quartz port of a pressure suit, the grey basalt rocks would appear sepia-toned. The white paint on the lander looked yellow, the blue paint looked black. It was a visual confirmation of the chemical prison the planet had become. However, the Venera 14 mission provided a moment of grim, mechanical irony that has become legendary in the annals of space exploration. The lander was equipped with a spring-loaded arm designed to measure the compressibility of the soil, essentially to punch the ground and see how hard it was. This was a critical measurement for understanding the surface density. Upon landing, the pyrotechnics fired to eject the camera lens caps. In a twist of fate that defies statistical probability, the ejected lens cap caught the dense Venusian wind, flipped through the air, and landed directly on the spot where the compressibility arm was programmed to strike. When the arm deployed a moment later, it slammed down not onto the Venusian regolith, but onto the titanium lens cap. The telemetry beamed back to Earth indicated that the surface of Venus was exactly as hard as a Soviet-made camera cover. It was a maddening failure of a primary instrument, proving that even across millions of kilometers of vacuum, Murphy's Law remains a universal constant. Yet, the camera that had lost its cap continued to function, capturing the surrounding terrain in high fidelity, oblivious to the slapstick comedy occurring just beneath its field of view. The data from these cameras, combined with the chemical analysis from the onboard drills, painted a picture of a planet that was geologically alive but catastrophically broken. The rocks were confirmed to be tholeiitic basalt, similar to the rock found at mid-ocean ridges on Earth. This confirmed that Venus was a volcanic world. But the visual evidence of the sharp, uneroded rocks presented a paradox. On Earth, plate tectonics recycle the crust. Old rock is subducted, and new rock is born. Venus showed no signs of such plate movement. There were no subduction trenches visible in the panoramas, no folding mountains like the Himalayas. This led to the stagnant lid hypothesis. Without water to lubricate the subduction of tectonic plates, the crust of Venus seized up. The heat from the core, unable to escape through the constant conveyor belt of tectonics, builds up beneath the solid crust. Eventually, every few 100 million years, the pressure becomes too great. The entire planet undergoes a global resurfacing event. The crust cracks open, and the world is flooded with lava, burying everything and resetting the geological clock. The sharp rocks seen by Venera were likely the shattered remnants of the last time the planet turned itself inside out. The visual exploration of Venus also reshaped our understanding of the horizon. On the Moon, with no atmosphere, the horizon is a crisp black line. On Earth, it is often blue and hazy. On Venus, the refraction is so intense due to the atmospheric density that light actually bends around the curvature of the planet. In theory, if you could see far enough, the back of your own head would be visible. In the Venera panoramas, the horizon appeared distorted, curving upwards slightly, creating the optical illusion that the lander was sitting at the bottom of a shallow bowl. This fisheye effect was not a lens distortion, but a physical property of the atmosphere itself. These panoramas remain unique in human history. Since 1985, no lander has returned images from the surface. The technological hurdle is simply too high for the current budget priorities of space agencies. To build a camera that can survive 475 degrees Celsius without active cooling requires semiconductor technologies, such as silicon carbide electronics, that are only now maturing. The Soviet method of brute force cooling, or using a melting thermal mass, limited the missions to roughly an hour. To get a video, to watch the wind move the dust or see the shadows shift with the sun, requires a lander that can survive for days. The legacy of the Venera cameras extends beyond planetary science. It touches on the philosophical. Those grainy, line-scanned images are our only window into the anti-Earth. They show us the inevitable result of a runaway greenhouse effect. They transform the abstract data of 90 atmospheres and sulfuric clouds into a tangible place. A place with a horizon, with rocks, with a sky. They ground the hellish conditions in reality. The silence that followed the Venera program has lasted for 40 years. While radar mapping orbiters like Magellan have stripped the planet of its secrets from above, revealing the global distribution of volcanoes and rift valleys, they lack the intimacy of the view from the ground. Radar cannot show you the colour of the sky or the texture of a rock. It cannot replicate the visceral feeling of standing there. The Venera images serve as a haunting memento mori for planetary habitability. They remind us that the Goldilocks zone is fragile. Looking at the yellow skies of Venera 13, we are looking at a sister world that choked on its own atmosphere. The rocks, sharp and menacing, are a testament to a geological violence that dwarfs anything on Earth. And the mechanical eyes that took them, now melted and crushed, slowly corroding into the basalt, stand as the only monuments humanity has ever erected in the fire. As we look toward the future, new missions like Da Vinci, Deep Atmosphere Venus investigation of noble gases, chemistry and imaging, aim to return. Da Vinci plans to drop a descent sphere that will capture high-resolution images during its fall, bridging the gap between the orbital radar and the surface. But a true successor to the Venera landers, a rover or a long-duration static station, remains on the drawing board. Until we return, the Soviet panoramas are all we have. They are grainy, distorted and coloured by the limitations of 1970s technology, but they possess an eerie beauty. They are the only proof that we once touched the surface of the morning star and found it to be a place of terrible majesty, a place where the air is an ocean, the rain is acid, and the ground waits for the next great fire to wash it clean. The camera innovation was not just a technical victory, it was an act of defiance, stealing a glimpse of a world that was never meant to be seen. Venera 9, launched in June 1975, was a massive leap forward in complexity. It consisted of two parts, an orbiter that would relay signals back to Earth and a lander designed to reach the surface. The lander was a 2-meter tall structure topped with a helical antenna and an aerodynamic braking shield. At its heart sat the pressure vessel, the titanium sphere containing the delicate electronics and the telephotometer. The descent profile was a choreographed sequence of braking and shedding weight. The lander would hit the atmosphere at immense speed, protected by a heat shield. Once the speed dropped, a series of parachutes would deploy to stabilize the craft and drag it through the cloud layers. However, unlike previous missions where the parachute carried the probe all the way down, Venera 9 was designed to cut the parachute loose at an altitude of 50 kilometers. The atmosphere near the surface was so thick, comparable to water, that the lander could rely on a rigid circular air brake to slow its fall. This minimized the time spent in the roasting air, rushing the probe to the ground to maximize its survival time on the surface. On October 22, 1975, the theoretical architecture of Venera 9 faced the brutal reality of execution. After a 4-month cruise through the vacuum of space, the moment of separation arrived. The orbiter, a massive bus of sensors and relay antennas, released the descent module 2 days before encountering the planet. This timing was critical. The lander needed to enter the atmosphere at a precise angle. Too shallow, and it would skip off the upper atmosphere like a stone on a pond. Too steep, and the G-forces would crush the instrumentation before the heat shield could do its work. The sphere, chilled to -10 degrees Celsius by the orbiter's circulatory system, began its lonely plunge into the clouds, severing its umbilical connection to the mothership. The entry velocity was 10.7 kilometers per second. When the lander hit the upper atmosphere, the deceleration was violent, peaking at 170 G. For a few terrifying seconds, the descent module weighed as much as a fully loaded jumbo jet. The ablative heat shield, composed of a honeycomb material filled with a resinous compound, vaporized sacrificially, carrying away the immense thermal energy generated by the shockwave. The air in front of the probe turned into a sheath of plasma, glowing brighter than the sun, blocking all radio communications. This was the blackout phase, a silence that mission control in Yevpatoria could only endure, waiting for the telemetry to return. As the speed dropped to subsonic levels, the automation took over. The pilot chute fired, pulling away the upper heat shield and dragging the main parachute from its canister. The lander swung beneath the canopy, drifting through the upper cloud deck at an altitude of 65 kilometers. Here, the conditions were deceptive. The pressure was less than 1 atmosphere, and the temperature was a manageable near freezing. But beneath this acid haze lay the true enemy. The clouds of Venus are not water vapor, they are concentrated droplets of sulfuric acid, a corrosive mist that would eat through ordinary metals and fabrics. The Venera lander, however, was wrapped in layers of glass-reinforced plastic and synthetic insulation, designed to shrug off the chemical attack. At an altitude of 50 kilometers, the mission profile diverged radically from all previous planetary explorations. The onboard computer, sensing the rising external pressure and temperature, fired explosive bolts. The main parachute, the lifeline that had steadied the craft, was jettisoned. To an observer, this would look like madness, dropping a stone into an abyss. But the atmosphere of Venus is not air as we know it. By the time the probe reached the lower altitudes, the carbon dioxide was compressed to a supercritical fluid. It had the density of liquid water but the viscosity of a gas. The rigid circular aerodynamic brake, a metal drag ring surrounding the antenna, caught this thick atmosphere. The lander did not fall, it sank. It drifted down like a bathyscarp descending into the Mariana Trench, controlled not by fabric, but by the sheer resistance of the fluid atmosphere against the metal ring. This free-fall phase was calculated to last exactly 50 minutes. Any longer, and the heat would soak through the insulation before touchdown. Any shorter, and the impact would destroy the instruments. During this descent, the sensors tasted the air. They detected chlorine, sulfur, and traces of water vapor, confirming the complex and toxic chemistry of the greenhouse world. The nephelometers, cloud sensors, made a startling discovery. The clouds were not a solid block down to the surface. There were distinct layers. Between 60 and 50 kilometers, the haze was thick. But below 30 kilometers, the air suddenly cleared. The probe emerged from the bottom of the cloud deck into a vast, pressurized, clear zone. The temperature outside was now climbing past 300 degrees Celsius, and the pressure was passing 50 atmospheres. Touchdown occurred on the slopes of Beta Regio, a region suspected to be a massive volcanic uplift. The landing speed was 7 meters per second. A hard slam, equivalent to dropping the probe from a 2-story building on Earth. The shock absorbers, essentially toroidal metal crush rings, deformed instantly to absorb the kinetic energy. The lander settled, tilted slightly on the rocky slope. The telemetry signal remained strong. It had survived the fall. Now began the race against thermodynamics. The internal temperature was slowly rising as the heat from the 475 degrees Celsius environment began to bleed through the insulation. The lithium nitrate trihydrate heat sinks began to melt, frantically absorbing energy to keep the CPU and transmitter cool. The lander had, at best, 60 minutes before thermal death. The primary objective was the eyes. Venera 9 was equipped with 2 telephotometers, designed to provide a 360-degree panoramic view. The covers protecting the quartz portholes were held in place by metal pins. Pyrotechnic charges fired to blast them away. One cap blew off successfully, tumbling onto the alien rocks. The other failed to release, likely jammed by the differential thermal expansion of the metal casing. The probe was half blind, but one eye was open. The scanner began to move. Unlike a modern CCD camera that captures an entire image instantly, the telephotometer was a mechanical device. A mirror rocked back and forth, building the image pixel by pixel, line by vertical line, sweeping across the field of view. The data was encoded and beamed up to the orbiter, which was passing rapidly overhead. From the orbiter, the signal was relayed to the massive dishes in the Crimea. As the image materialized on the thermal paper in mission control, the scientist was stunned. The prevailing geological theory, based on the high atmospheric density, was that the surface of Venus would be a smooth, eroded desert. The logic was that the soup of the atmosphere would act like a tumbler, smoothing rocks into pebbles and filling craters with dust. Venera 9 refuted this instantly. The image showed a landscape of sharp, angular rocks. The ground was littered with flat, fractured stones casting long, distinct shadows. There was no sand, no dust dunes. The sharpness of the rocks implied that the surface was geologically young. These stones had not been sitting there for billions of years being eroded. They were fresh, likely broken by tectonic shifting or volcanic cooling. The presence of shadows was equally revelatory. It proved that the thick clouds did not block the sun entirely. Sunlight penetrated the haze, diffusing into a pervasive, omnidirectional glow, similar to a stormy afternoon on Earth. The visibility was surprisingly good. The horizon was clearly visible hundreds of meters away, curving slightly due to the extreme atmospheric refraction. For 53 minutes, Venera 9 transmitted. It measured the wind speed at the surface, a mere 0.5 meters per second. On Earth, this is a dead calm, but on Venus, with air that is nearly 100 times denser than Earth's, even this slow breeze carries the momentum of a flowing river. it would be enough to push a human being off balance. The microphone detected the sound of this wind, a low, oppressive drone, interrupted only by the creaking of the lander's metal skin as it expanded in the heat. The probe also conducted gamma-ray spectrometry on the rocks beneath it. The analysis returned a composition of tholeiitic basalt, chemically identical to the lava rocks found at mid-ocean ridges on Earth. This was the smoking gun for planetary volcanism. Beta Regio was not just a mountain, it was a shield volcano of immense proportions, and Venera 9 was sitting on its flank. As the minutes ticked by, the cooling capacity of the lithium salts reached its limit. The internal temperature of the pressure vessel began to climb. First, the delicate chemical sensors failed. Then, the telemetry from the camera became noisy as the thermal noise overwhelmed the signal. Finally, the radio transmitter itself succumbed to the heat. The carrier wave ceased. Venera 9 fell silent, its mission complete. It had transformed Venus from an abstract concept into a physical place, a world of grey basalt, crushing pressure, and eerie, shadow-filled twilight. The orbiter continued to circle the planet, relaying the stored data back to Earth, but the lander was now just another rock on the surface. However, the architecture of the mission had been vindicated. The drop-and-sink strategy, using the atmosphere itself as a brake, became the standard for all future Soviet missions. The success of the air brake ring proved that on Venus, aerodynamics and hydrodynamics blur. The legacy of Venera 9 went beyond the data. It was a psychological victory. It proved that the surface of hell was a navigable destination. The image it returned, that grainy black and white strip of alien ground, remains one of the most significant photographs in the history of science. It showed that even in the most hostile environment in the solar system, a robot built by human hands could open its eye and see. The mission also highlighted the stark difference between Earth and its twin. Both planets are made of the same stuff, situated in the same region of the solar system, yet one is a blue marble and the other a slate-grey oven. Venera 9 provided the ground truth for the greenhouse effect, offering a sobering lesson on planetary evolution. In the years that followed, the twin Venera 10 would replicate the feat, landing thousands of kilometers away and finding similar basaltic plains. But Venera 9 was the pathfinder. It demonstrated that complex operations, pyrotechnics, mechanical scanning, high-gain transmission, were possible in an environment that melts lead. It paved the way for the color cameras and drilling rigs of Venera 13 and 14. Today, the titanium skeleton of Venera 9 still sits on the slope of Beta Regio. The heat would have long since destroyed its internals, and the acid would have etched the glass of the porthole. But the pressure vessel likely remains intact, a silent monument to the engineering audacity of 1975. On October 22, 1975, Venera 9 survived the descent. It impacted the surface at roughly 7 meters per second, cushioned by a crushable metal torus at its base. The landing site was a steep slope of roughly 20 degrees, covered in loose tectonic debris. Inside the sphere, the tape recorders began to spin, and the telephotometer started its mechanical scan. The engineers had prepared for the worst-case scenario regarding visibility, assuming the thick clouds would block all sunlight. The lander carried halogen floodlights, but when the lens cap popped off, the sensors detected immediate illumination. The floodlights were unnecessary. The surface of Venus was not dark. The ambient light levels were comparable to a cloudy summer day in Moscow. The thick atmosphere scattered the sunlight evenly, creating a soft, diffuse glow that eliminated harsh shadows but provided ample light for the scanner. As the data arrived on Earth, line by line, a picture began to form on the thermal paper in mission control. It was not the sandy desert or smooth, eroded landscape that geologists had predicted. The image showed sharp, angular rocks. The edges were jagged and fresh, implying that the surface was geologically young and that the wind speeds at ground level were negligible. The horizon was visible in the corners of the frame, proving the air was clear of dust. Humanity was looking at the surface of another world. The transmission of this single, panoramic image was a slow, agonizing revelation that shattered decades of planetary theory in mere minutes. As the mechanical scanner swept back and forth, building the picture pixel by pixel, the scientists at the Soviet Institute of Space Research were not merely looking at rocks, They were looking at the tombstone of the wet Venus hypothesis. The sharpness of the stones was the most immediate and jarring contradiction to established models. On Earth, or Mars, a chaotic pile of rocks on a slope would eventually be smoothed by the elements. Wind carrying abrasive dust acts as sandpaper over geological timescales. Water, if it existed, would tumble sharp edges into rounded pebbles. The rocks of Beta Regio, however, looked as though they had been shattered yesterday. They were slab-like, some spanning dozens of centimetres, resting on a darker soil-like substrate. This lack of erosion implied a terrifying stillness. Despite the atmosphere being a supercritical fluid with the density of water, the surface winds were evidently too sluggish to pick up significant particulate matter. The anemometer on board Venera 9 confirmed this, measuring a wind speed of only 0.5 to 0.9 metres per second. While a breeze of this speed on Earth would be negligible, in the 90 bar pressure of Venus, it carried the momentum of a flowing river. It was a slow, crushing current, yet it lacked the turbulence required to erode the hard basaltic crust. The jaggedness of the terrain suggested that the surface was geologically young, likely the result of relatively recent tectonic fracturing or volcanic explosive activity. Venus was not a dead static swamp. It was a planet that was geologically alive, perhaps violently so, capable of breaking its own crust and leaving the shards to bake in the eternal heat. Beyond the visual spectrum, Venera 9 was busy tasting the world it had invaded. The lander was equipped with a gamma-ray spectrometer, a device designed to detect the radioactive decay of elements within the soil. By measuring the ratios of potassium, uranium and thorium, the instrument could identify the type of rock beneath the lander's shock ring. The data returned a clear signature: tholeiitic basalt. This was a profound discovery. Tholeiitic basalt is the most common volcanic rock in the solar system, forming the bedrock of Earth's ocean floors and the vast mare plains of the Moon. Its presence on Venus confirmed that the planet was differentiated, possessing a mantle and a crust similar to Earth's, and that it had been shaped by massive volcanic outpourings. The slope Venera 9 rested upon was likely the flank of a massive shield volcano, or the debris apron of a tectonic rift zone. The optical properties of the atmosphere also provided a wealth of unexpected data. The horizon visible in the upper corners of the panorama appeared curved, but not because of the planet's shape or the camera lens alone. The sheer density of the carbon dioxide atmosphere creates a phenomenon known as superrefraction. On Earth, the atmosphere bends light slightly, allowing us to see the sun for a few minutes after it has physically set. On Venus, this effect is amplified to a hallucinogenic degree. Light rays are bent around the curvature of the planet. Theoretical models suggest that if the air were perfectly clear, a standing observer might see the back of their own head as light circled the globe. In reality, the haze limits visibility to a few kilometers, but the refraction creates an optical illusion where the ground appears to bowl upwards, making the observer feel as though they are standing at the bottom of a vast, shallow crater. Venera 9's images showed a horizon that felt oppressive and enclosing, a visual manifestation of the trap that is the Venusian surface. As Venera 9 worked, its twin, Venera 10, was preparing for its own arrival. Launched only days apart, Venera 10 touched down on October 25, 1975, approximately 2,200 kilometers away from its sibling. The contrast between the two landing sites provided a crucial stereogeological perspective. While Venera 9 had landed on a steep scree-covered slope of roughly 30 degrees, Venera 10 touched down on a flat, expansive plain. The rocks here were different. Instead of jagged, broken slabs, the surface was paved with flat, pancake-like outcrops of bedrock, separated by veins of dark soil. These formations appeared weathered, perhaps not by wind, but by chemical corrosion. The concept of weathering on Venus took on a new, sinister meaning. It wasn't physical abrasion, it was a chemical attack. The rocks were interacting with the sulfur and carbon dioxide in the atmosphere, slowly transforming into softer minerals that could be crumbled by the thermal expansion and contraction of the day and night. The success of Venera 10 reinforced the basaltic findings of Venera 9, confirming that the volcanic composition was global, not local. However, both missions shared a singular, maddening mechanical failure that highlighted the extreme difficulty of operating in such an environment. Both landers were equipped with 2 cameras to provide a full 360-degree panorama. On both landers, the protective lens cap on one of the cameras failed to eject. Whether due to the immense external pressure jamming the mechanism, or the thermal expansion of the locking pins, the result was that both probes were half-blind, returning only 180-degree strips of the landscape. It was a testament to the redundancy built into Soviet engineering. Had they flown only one camera, the missions might have been total visual failures. Instead, they were partial triumphs. The lifespan of Venera 9 on the surface was dictated by thermodynamics. The lander was essentially a dying creature from the moment it separated from the orbiter. Its lifeblood was the latent cold stored in its structure, and the phase change capability of the lithium nitrate trihydrate heat sinks. For 53 minutes, the lander waged a war against the second law of thermodynamics. The heat of Venus, at 485 degrees Celsius, relentlessly pushed inwards, seeking equilibrium. It soaked through the layers of glass wool insulation, warming the titanium pressure shell. It conducted through the landing struts and the camera ports. Inside the sphere, the temperature began to rise. First, the most sensitive atmospheric sensors began to drift, their calibrations warped by the heat. Then, the noise in the telemetry stream increased as the thermal agitation of electrons in the transmitter circuits grew. The engineers in Yevpatoria watched the signal strength fluctuate. They knew the end was coming not because of a battery failure, but because the machine was cooking from the inside out. The orbiter overhead, acting as the relay station, was also moving out of radio range, dipping below the horizon relative to the lander. It is a subject of debate which severed the link first, the geometry of the orbits or the death of the lander's electronics, but the result was the same. After nearly an hour of operation, Venera 9 fell silent. The silence that followed was different from the silence of failure. It was the silence of a job completed. The data packet Venera 9 sent home was finite, but its implications were infinite. It forced a complete rewrite of planetary science textbooks. The swamp was gone. The oil ocean was gone. In their place was a planet that served as a grim mirror to Earth. Venus was not a younger primitive Earth. It was an evolved terminal Earth. It demonstrated the end state of a greenhouse effect run amok, the carbon that Earth had successfully sequestered in limestone, and life had remained atmospheric on Venus, roasting the planet. The geological data proved that a planet could be volcanically active without having plate tectonics. The stagnant lid theory of Venusian geology, where heat builds up under a solid crust until the whole planet catastrophically resurfaces, gained traction from the evidence of the young, sharp rocks seen by Venera 9. Moreover, the mission marked a psychological turning point in the Cold War space race. While the Americans were preparing the intricate Viking landers for Mars to search for life, the Soviets had successfully assaulted a world that was inherently hostile to the very concept of life. They had demonstrated a mastery of heavy industrial materials science, titanium welding, high-temperature metallurgy, and hermetic sealing that was unmatched. The Venera landers were not delicate scientific instruments wrapped in foil. They were submarines built to dive into a sea of fire. The legacy of Venera 9 is physically present on the surface of Venus today. The lander sits on the slope of Beta Regio, a permanent artifact of human ingenuity. The harsh environment has undoubtedly taken its toll over the decades. The optical quartz of the camera port has likely been etched opaque by the sulfuric acid clouds and the interaction with fluorine compounds in the atmosphere. The external paint stripped away would leave the titanium shell bare. The aluminum landing ring has likely corroded or melted if the temperature spiked even slightly higher than recorded, but the pressure vessel itself remains. Titanium is remarkably resistant to corrosion and melts at over 1600 degrees Celsius, far above the ambient temperature of Venus. Barring a volcanic eruption or a seismic landslide, Venera 9 sits exactly where it landed, a metal sphere in the eternal gloom. It is a monument to the 53 minutes when humanity first opened its eyes in hell. The mission proved that there is no environment in the solar system so hostile that it cannot be touched, provided one has the engineering audacity to build a machine that can endure it. The blurry, line-scanned image of those sharp, grey rocks remains one of the most haunting photographs ever taken, a testament to a world that could have been Earth, and a warning of what Earth could become. The exploration of Venus did not end with Venera 9, but the romantic mystery of the planet did. The cloud-shrouded goddess was unveiled, and beneath the veil was a face of stone and fire. Three days later, Venera 10 arrived at the planet. Its mission profile was identical to its twin, but it targeted a different landing zone to provide a comparative geological sample. it touched down over 2,000 kilometers away from the Venera 9 site. Where the first probe had landed on a steep rocky slope, Venera 10 settled onto a vast flat plain. The images returned by Venera 10 showed a landscape that was dramatically different from the first. Instead of a debris field of sharp rocks, the camera revealed flat, pancake-like slabs of rock that resembled dried magma flows. The ground was smoother, weathered, and darker. This contrast was scientifically vital. It proved that Venus was not a uniform wasteland but a planet with distinct geological regions, mountains, and plains. The probe operated for 65 minutes before the heat finally overwhelmed the transmitter, adding another priceless strip of data to the archives. The synchronized success of Venera 9 and Venera 10 marked the zenith of the early photographic era of Venusian exploration, fundamentally altering our understanding of the planet's geology. By placing two landers in distinctly different geological provinces, one in a tectonic rift zone and the other on a vast volcanic plain, the Soviet scientists could for the first time engage in comparative planetology. The data from Venera 10, though chemically similar to its twin, told a different structural story. The gamma-ray spectrometer on board identified the flat, pancake-like slabs as tholeiitic basalt, but their morphology suggested a different history. Unlike the sharp, jagged detritus of the Venera 9 site, which implied recent tectonic fracturing, the rocks at the Venera 10 site appeared aged. They were smoothed not by water or wind, but likely by the corrosive weathering of the atmosphere itself. In the hyper-pressurized, chemically reactive cauldron of the surface, minerals are unstable. Sulfur and carbon dioxide slowly eat away at the crystalline structure of the rock, a process known as chemical weathering, leaving behind the hardened, flat outcrops observed by the lander. However, the triumph of these missions was tempered by a recurring mechanical curse that highlighted the extreme difficulty of operating in such a hostile environment. Both Venera 9 and Venera 10 were designed to provide a full 360-degree panoramic view of their surroundings using two independent telephotometers. On both landers, only one of the protective lens caps released. The other cap, held in place by a pyrotechnic pin, failed to eject. The leading theory is that the immense external pressure, 90 times that of Earth, compressed the seal so tightly that the explosive charge was insufficient to dislodge it, or perhaps the thermal expansion of the titanium casing jammed the mechanism. Consequently, both probes were half-blind, returning only 180-degree strips of the alien world. It was a stark reminder that on Venus, even the simplest mechanical action is a gamble against the laws of physics. Despite this partial blindness, the data gathered was transformative. The optical measurements confirmed a phenomenon that had long been theoretical: superrefraction. The atmosphere of Venus is so dense that it bends light around the curvature of the planet. In the images returned by Venera 10, the horizon appeared distorted, curving upward at the edges of the frame. This created a disorienting optical illusion, where the lander appeared to be sitting at the bottom of a vast shallow bowl. If the visibility were infinite, a person standing on Venus could theoretically see the back of their own head as light circled the globe. In reality, the dense haze limits visibility to a few kilometers, but the oppressive fish-eye quality of the horizon adds to the claustrophobic nature of the surface environment. The success of the 1975 missions paved the way for the final and most sophisticated generation of Soviet landers, Venera 13 and Venera 14, launched in 1981. If Venera 9 and 10 were about seeing, these new machines were about touching and listening. They were heavier, smarter, and armoured with even more robust thermal protection systems. Their goal was to capture the world in colour and to perform the audacious feat of drilling into the surface rock to analyse its chemical composition directly. On March 1, 1982, Venera 13 touched down in the Phoebe Regio region. It survived for a record-breaking 127 minutes, more than double its design life. The colour images it returned were breathtaking and deeply unsettling. They revealed a world bathed in a suffocating, sickly orange light. The thick atmosphere of Venus acts as a massive blue blocking filter. The Rayleigh scattering that gives Earth its blue sky is overwhelmed by the sheer volume of gas and suspended sulfur particles. Blue light is scattered and absorbed long before it reaches the ground, leaving only the red, orange and yellow wavelengths to illuminate the surface. To ensure accurate colour reproduction, the landers carried a colour calibration chart, a strip of blue, green, red and white paint. In the raw images, the white paint appeared yellow and the blue paint appeared almost black. This confirmed that if a human astronaut were to stand on Venus looking through a clear visor, the grey basalt rocks would appear sepia-toned, and the sky would be a heavy, glowing apricot dome, devoid of any sun disk. The psychological impact of this colour palette, a world without cool tones trapped in an eternal heated twilight, cemented Venus's reputation as a hellscape. Venera 13 also carried a microphone, allowing humanity to hear the sounds of another world for the first time. It did not record the howling, chaotic gales that science fiction had imagined. Instead, it captured a low, steady drone. The wind on the surface of Venus moves slowly, rarely exceeding 1 meter per second. However, because the air is so dense, even a slow breeze carries the momentum of a rushing river. The microphone also recorded the sharp, metallic crack of the lander's structure settling and warping under the thermal shock, a lonely sound of a machine dying in the heat. 4 days later, Venera 14 arrived, landing in a region of smooth basaltic plains similar to the Venera 10 site. It was here that the program experienced its most infamous moment of tragic comedy. The mission profile called for a spring-loaded arm to swing out and strike the ground to measure the compressibility of the soil. Simultaneously, the camera lens caps were ejected to clear the view. In a twist of fate that defies statistical probability, the ejected lens cap caught the dense wind, flipped through the air, and landed directly on the spot where the compressibility arm was programmed to strike. When the arm deployed a moment later, it slammed down not onto the Venusian regolith, but onto the titanium lens cap. The telemetry beamed back to Earth indicated that the surface of Venus was exactly as hard as a Soviet-made camera cover. It was a maddening failure of a primary instrument, proving that Murphy's law is a universal constant. However, the camera that had lost its cap continued to function, capturing the surrounding terrain in high fidelity, oblivious to the slapstick accident occurring just beneath its field of view. Despite the lens cap incident, the drilling mechanisms on both Venera 13 and 14 were successful. This was an engineering marvel in itself. Drilling requires lubrication, but standard oils would instantly vaporize or combust at 475 degrees Celsius. The Soviet engineers developed a unique drilling rig that operated without liquid lubricants, using high-temperature solid bushings and relying on the thermal expansion of the metal to create the necessary seals. The drill bit penetrated 3 centimeters into the rock, sucked the powdered sample into a vacuum airlock, and transferred it to an internal chamber for X-ray fluorescence analysis. The chemical results were surprising. While Venera 14 found tholeiitic basalt similar to the previous missions, Venera 13 found a rare type of rock known as lucite basalt, which is rich in potassium. On Earth, this rock is associated with deep volcanic anomalies and subduction zones. Its presence on Venus suggested that the planet's geology was far more complex and varied than a simple, global lava ocean. It hinted at a differentiated crust and a history of evolved magmatic processes that we still do not fully understand. The legacy of the Venera program is defined by these final, high-fidelity glimpses. After the Vega missions in 1985, which deployed balloons into the upper atmosphere but did not focus on surface imaging, the exploration of the Venusian surface ceased. The collapse of the Soviet Union brought an end to the only space program dedicated to the comprehensive study of Venus. For 40 years, no new images have been sent from the surface. The artifacts of this era remain there today. The titanium pressure vessels of Venera 9, 10, 13 and 14 sit silently on the plains of Beta Regio and Phoebe Regio. The intense heat would have long since equalized, frying their internal electronics. The sulfuric acid in the atmosphere, though mostly dissociated at surface levels, would have slowly etched the optical quartz and corroded the external sensors. The paint would have peeled away, leaving dull grey metal, but barring a volcanic eruption or a seismic landslide, the heavy structures are likely intact. They are the only human footprints on a world that serves as a grim mirror to our own. These missions revealed a planet that is the antithesis of the biological Earth. It is a world where the atmosphere is an ocean, the rain is acid, and the geology is locked in a stagnant, heated cycle. The wet swamp of Victorian imagination was replaced by a reality that is far more scientifically compelling and terrifying. The Soviet engineers proved that with enough armor, enough thrust, and enough audacity, humanity could touch the most hostile environment in the solar system. They turned a point of light in the sky into a physical place, a place of orange skies, crushing pressure, and silent heavy winds, and in doing so, they completed one of the greatest engineering sagas in history. The silence that now covers the Venusian plains is not one of mystery, but of a question answered. We know what is there, and it is a warning. The combined data from these two missions revolutionized the understanding of Venus. The detailed analysis of the surface rocks visible in the panoramas suggested a basaltic composition, similar to the volcanic rocks found on the ocean floor of Earth. This confirmed that Venus was a planet driven by volcanism. The sharpness of the rocks at the Venera 9 site was particularly telling. In a dense atmosphere, wind and sand should scour rocks smooth over time. The fact that these rocks were jagged meant they had not been exposed to the elements for long, or that the surface environment was incredibly static. Atmospherically, the images solved the mystery of visibility. The lid of clouds was located high in the atmosphere, but the air at ground level was transparent. There was no fog. The refraction of light through the dense gas created a strange optical illusion where the horizon appeared to curve upward, making the viewer feel as though they were standing in the bottom of a bowl. This distortion, combined with the soft, scattered light, gave the Venusian surface a surreal, underwater quality. However, the black and white images from Venera 9 and 10 left a crucial question unanswered: the colour of this alien world. The human eye relies on colour to interpret depth, mineral composition, and atmospheric conditions. Without it, the scientists were looking at a monochrome etching of a nightmare. The physics of the atmosphere suggested that the surface should be bathed in a deep, suffocating red. But confirmation required a new generation of technology. The heavy filtration of solar radiation by the cloud deck meant that the blue end of the spectrum was likely entirely absent. The Rayleigh scattering that gives Earth its azure sky would be overwhelmed on Venus by the sheer volume of carbon dioxide and the sulfuric acid droplets, which act as a massive blue-blocking filter. To a standing observer, the sky would not be blue nor black, but a heavy, glowing dome of diffuse apricot light. This hypothesis was confirmed 7 years later, in March 1982, with the arrival of Venera 13 and 14. These landers represented the zenith of the Soviet planetary program, machines built not just to see, but to interpret the chromatic reality of hell. They carried colour cameras and, crucially, colour calibration charts, strips of blue, green, red, and white paint attached to the lander's casing. When the first colour panoramas arrived in Moscow, the results were startling. The white paint on the chart appeared distinctly yellow. The blue paint appeared almost black. The processing algorithms revealed that the surface of Venus is trapped in an eternal sepia-toned twilight. There are no cool colours on Venus. The rocks, which spectral analysis later identified as grey basalt, appeared rusty and brown. The pervasive orange glow softens the landscape, reducing contrast and stripping the world of the visual cues we associate with a natural environment. It is a world lit by the embers of a dying fire. Beyond the optics, the geological implications of the Venera findings began to coalesce into a terrifying theory of planetary evolution. The sharp, uneroded rocks seen by Venera 9, contrasted with the flat plate-like formations at the Venera 10 and 14 sites, pointed to a planet that was geologically schizophrenic. On Earth, the crust is constantly recycled through plate tectonics. Old crust is subducted, melted, and reborn as new land. This process acts as a thermostat, regulating the planet's internal heat and atmospheric carbon. Venus, the data suggested, lacks this conveyor belt. It appears to be a stagnant lid planet. Without water to lubricate the subduction zones, the crust of Venus seized up eons ago. The heat from the radioactive core, unable to escape through the constant movement of plates, builds up beneath the solid, immovable crust. The pressure mounts for hundreds of millions of years until the planet reaches a breaking point. The prevailing theory, supported by the surface imagery, is that Venus undergoes catastrophic global resurfacing events. The entire crust effectively melts or fractures, and the planet turns itself inside out in a paroxysm of volcanism that can last for millennia. The sharp rocks of Venera 9 were likely the shattered remnants of the last great upheaval, a fresh scar on a planet that periodically destroys its own history. To confirm this volcanic nature, the engineers of Venera 13 and 14 attempted the impossible: drilling. The challenge of mechanical drilling in an environment of 475 degrees Celsius and 90 atmospheres is a nightmare of tribology. the science of friction and lubrication. Standard machine oils vaporize instantly or combust on Venus. The differential thermal expansion of metals means that a steel drill bit and a titanium casing will expand at different rates, causing the mechanism to seize. The Soviet solution was to use exotic dry lubricants, such as molybdenum disulfide, and to design the drill with slop, intentional loose tolerances that would tighten to a perfect fit only when the machine heated up to the ambient temperature of the surface. Venera 13's drill deployed successfully, humming against the bedrock. It bored 3 centimeters deep, chewed up the basalt, and then performed a vacuum suction maneuver to pull the hot dust into a specialized airlock. Once inside the pressure vessel, the sample was fed into an X-ray fluorescent spectrometer. The machine worked. It identified the rock as lucite basalt, a rare, potassium-rich volcanic rock found on Earth in regions of intense tectonic activity, such as the Mediterranean islands. This proved that Venus was not just a ball of simple lava. It had undergone complex chemical differentiation. It was a rocky world with a mantle and crust similar to Earth's, but one that had taken a divergent, catastrophic path. However, the drilling experiment on Venera 14 provided one of the most infamous moments of tragic comedy in the history of space exploration. The lander touched down perfectly on a flat basaltic plain. The pyrotechnic charges fired to eject the camera lens caps. In a twist of fate that defies statistical probability, the ejected lens cap caught the dense, heavy wind, flipped through the air, and landed precisely on the spot where the spring-loaded compressibility arm was programmed to strike. When the arm deployed a moment later to test the hardness of the Venusian soil, it slammed down not onto the rock but onto the titanium lens cap. The telemetry beamed back to Earth indicated that the surface of Venus was exactly as hard as a Soviet camera cover. It was a maddening failure of a primary instrument, a reminder that even across millions of kilometers of vacuum, Murphy's Law remains a universal constant. Yet, perhaps the most haunting data returned by these final missions was not visual or chemical, but acoustic. Venera 13 and 14 carried microphones. For the first time, human ears heard the sound of another world. The scientists did not hear the howling, chaotic gales that fiction writers had imagined. The atmosphere of Venus is too thick for high-speed turbulence at ground level. Instead, the microphones recorded a low, heavy drone, the sound of a viscous fluid moving slowly but with immense momentum. The wind speed was measured at only 0.3 to 0.6 meters per second, a mere gentle breeze by Earth standards. But in an atmosphere 90 times denser than air, this slow wind pushes with the force of a flowing river. It is a crushing, steady pressure. The audio recording also captured the sharp, metallic crack of the lander's structure settling. As the titanium shell heated up, it expanded, groaning under the thermal stress. This was the sound of the machine dying. It was a lonely mechanical rhythm, the low hum of the wind, the whir of the cooling fans fighting a losing battle, and the cracking of metal in the heat. It was the acoustic signature of a dead world. The final chapter of this surface exploration came with the Vega missions in 1985, which shifted focus from the ground to the sky. While the landers died in an hour, the Vega balloons floated in the upper atmosphere for days. These aerobots revealed that while the surface is a stagnant oven, the atmosphere is a chaotic engine of super-rotation. At an altitude of 50 kilometers, where the pressure and temperature are remarkably Earth-like, the winds whip around the planet at 300 kilometers per hour, circling the globe in just 4 days. This atmospheric disparity, a stagnant surface and a hurricane-force upper atmosphere, remains one of the great unsolved mysteries of planetary dynamics. The legacy of the Venera program is physically present on the surface of Venus today. The landers, Venera 9, 10, 13, and 14, sit silently on the plains of Beta Regio and Phoebe Regio. The intense heat would have long since equalized, frying their internal electronics and turning their circuits into fused lumps of silicon and copper. The sulfuric acid in the atmosphere, though mostly dissociated at surface levels, would have slowly etched the optical quartz of the camera ports, blinding them forever. The paint would have peeled away, leaving dull grey metal exposed to the gloom. But barring a volcanic eruption or a seismic landslide, the heavy structures are likely intact. Titanium is incredibly resistant to corrosion and melts at over 1,600 degrees Celsius, far above the ambient temperature of Venus. The pressure vessels stand as silent sentinels, the only human footprints on a world that serves as a grim mirror to our own. They are monuments to the brute force era of discovery, where the only way to understand the environment was to build a tank and throw it into the fire. These missions did more than just map a planet. They recalibrated our understanding of habitability. They showed that the Goldilocks zone is not a guarantee of life, but a fragile possibility. Venus and Earth are twins in size, composition, and location. Yet, a slight variation in atmospheric history sent one down a path of blue oceans, and the other down a path of runaway greenhouse warming. The surface revealed by the Soviets was a warning. It demonstrated that a planet's atmosphere is a powerful self-reinforcing machine. Once the carbon cycle breaks, the planet turns into an oven. The data from Venera remains the bedrock of our knowledge. Every modern climate model of Venus, every proposal for a future rover, is built upon the hard-won telemetry of those few minutes in the 1970s and 80s. We know the rock is basalt because Venera tasted it. We know the sky is orange because Venera saw it. We know the wind hums because Venera heard it. The silence that has fallen over the Venusian plains for the last 40 years is not due to a lack of interest, but a testament to the immense difficulty of the challenge. The Soviets proved it was possible, but they also proved the cost. To return, we will need materials that can think in the heat, electronics that function inside a furnace, and the same audacity that drove the designers at Lavochkin to look at the brightest star in the sky and decide to touch it. Until then, the Russian robots remain the sole guardians of the surface, slowly weathering in the dark, heavy wind, waiting for the next visitor to arrive. The images that appeared in newspapers in 1975 were grainy and high contrast, but this was a limitation of the printing technology, not the data itself. The raw telemetry from the probes was a digital stream of brightness values. To create a viewable image, this data had to be converted into a raster format. The Soviet scientist had to correct for the geometric distortion caused by the scanning mirror and the panoramic perspective. Because the camera scanned in a wide arc, the raw image appeared warped. Straight lines became curved, and the horizon bent unnaturally. Mathematical algorithms were applied to flatten the image and correct the perspective, allowing geologists to measure the true size and distance of the rocks. The dynamic range of the telephotometers was surprisingly good, capturing details in both the bright highlights of the rock faces and the deep shadows of the crevices. This raw data stream was transmitted via a pulse code modulation (PCM) system, a method that sliced the continuous voltage from the photometer into discrete digital steps. However, the constraints of 1970s interplanetary bandwidth meant that simply sending a linear stream of brightness values was inefficient. The Soviet engineers employed a logarithmic quantization scheme for the Venera landers. In a linear system, the difference between a brightness value of 10 and 11 is the same as between 200 and 201, but on Venus, the illumination was an unknown variable. The camera might need to resolve the subtle texture of a dark basaltic rock in deep shadow just as clearly as the glare of the metallic landing ring under the floodlights. Logarithmic encoding compressed the data, allocating more bits to the darker end of the spectrum where the human eye and geological analysis craves detail. This allowed the 6-bit and later 9-bit on Venera 13 and 14 systems to achieve a perceived dynamic range that rivaled much higher bandwidth systems, but it also meant that the raw data, if visualized directly without a logarithmic decompression curve, would look washed out and bizarrely flat. The transmission itself introduced a layer of corruption that required sophisticated digital forensics to remove. The signal had to punch through the thick, electrically charged atmosphere of Venus, travel millions of kilometers across the inner solar system, and be caught by the deep space network dishes in Crimea and Yevpatoria. During this journey, the signal was subjected to cosmic noise, solar interference, and the inevitable attenuation of distance. When the data arrived, it was often speckled with salt and pepper noise, random bit flips where a 0 became a 1 or vice versa. In a text message, a wrong bit is a typo. In an image, it is a bright white or pitch black pixel that destroys the texture of the rock. To combat this, Soviet mathematicians utilized early forms of noise reduction algorithms. Since the image was built line by line, they could compare adjacent pixels. If a pixel's brightness value deviated statistically significantly from its neighbors, a spike, it was identified as noise and replaced with an average of the surrounding values. This was a delicate balance. Smooth the image too much, and you erase the geological grit and grain that proves the surface is made of rock and not sand. Smooth it too little, and the surface looks like static. The grainy look of the newspaper prints was often a result of over-sharpening these corrected images for high-contrast lithography, whereas the original digital files possessed a much smoother, more natural tonal gradation. A peculiar artifact of the Venera telemetry architecture was the inclusion of engineering data directly into the image stream. The bandwidth was so precious that the Soviets could not afford separate channels for system health, temperature, pressure, battery voltage, and image data. Instead, they interleaved them. In the raw images from Venera 9 and 10, and especially in the later colour missions, one can see distinct vertical bars or patterns of white blocks superimposed over the landscape. These were not alien artifacts or camera malfunctions. They were binary code representing the lander's vital signs, physically overwriting the visual data. Recovering the lost parts of the landscape beneath these telemetry bars required interpolation. In the 1970s, this was often done by simple retouching, essentially painting over the bars with the colour of the surrounding rocks. However, modern reprocessing of the original tapes by researchers like Don Mitchell has utilised advanced in-painting algorithms. These algorithms analyse the texture and directionality of the surrounding rock features to probabilistically predict what lies beneath the telemetry strips, reconstructing a seamless panorama that offers a more immersive view than the scientists of the Soviet era ever saw. The challenge of colour processing, introduced with Venera 13 and 14 in 1982, added an entirely new dimension of difficulty. The cameras did not capture colour instantly like a modern Bayer filter sensor. Instead, they used a filter wheel. The scanner would take a pass with a red filter, then the mechanical head would reset, the wheel would turn, and it would scan again with a green filter, and finally with a blue one. This sequential imaging meant that a full-colour photograph was actually a composite of 3 separate images taken over the course of several minutes. This introduced the problem of temporal parallax. While the rocks didn't move, the lighting conditions could change, or dust kicked up by the landing could settle between scans. If the sun angle shifted slightly due to the planet's rotation, though slow, or atmospheric flickering, the shadows in the red channel would not perfectly align with the shadows in the blue channel. Merging them required distinct alignment algorithms to prevent colour fringing, where rocks would appear to have ghostly red or blue edges. Furthermore, the true colour of Venus became a philosophical and technical debate. The raw data showed a world smothered in deep orange. The thick atmosphere absorbs blue light almost entirely. If you were standing on Venus, your eyes would indeed see an orange world. However, geologists needed to know the mineral composition of the rocks. To do this, they needed to strip away the atmospheric filter and see the rocks as they would appear under neutral white light, effectively Earth-lighting the scene. To achieve this, the landers carried colour calibration scales, strips of known pigments, white, grey, red, green, blue, attached to the landing ring within the camera's field of view. By measuring how the Venusian light distorted the known values of these paints, e.g. the white paint appearing yellow, the blue paint appearing black, scientists could calculate a transfer function. They could then apply the inverse of this function to the entire image, digitally removing the orange cast to reveal the dark grey basaltic nature of the rocks. This image processing step was crucial for identifying the soil as tholeiitic basalt. Without it, the iron-rich oranges of the atmosphere might have been mistaken for oxidized iron, rust, in the soil, leading to incorrect geological conclusions. The geometry of the scanning mechanism itself imposed a unique distortion known as the banana effect. The camera scanned by rotating a mirror through a vertical arc, while the head rotated horizontally. This meant the pixels were not arranged in a Cartesian grid, squares on a flat plane, but in a spherical coordinate system. When mapped directly to a flat computer screen, the horizon looked curved and the straight landing gear looked bent. To make the images geologically useful, they had to be projected. The most common projection was the azimuthal equidistant, or a cylindrical projection, which straightened the horizon but stretched the foreground. However, modern image processors have taken this a step further, mapping the data onto 3D models. By assuming the ground is relatively flat, a safe assumption for the immediate landing circle, the image data can be draped over a flat plane in a 3D rendering engine. This allows us to virtually stand next to the lander and look out at the horizon in a way that mimics natural human vision, correcting the fisheye distortion of the original mechanical scanner. Another layer of processing involved shape from shading. Because the atmosphere of Venus is a scattering medium, the light is incredibly diffuse. There are no harsh, crisp shadows like on the Moon. The shadows are soft and graduated. This makes it difficult to judge the depth of a rock or the steepness of a slope. However, the brightness of a surface on Venus is strongly correlated with its angle to the zenith, straight up. Horizontal surfaces are brightest, vertical surfaces are darker. By analysing the gradient of brightness across a single rock, algorithms can estimate its 3D shape, generating a depth map from a 2D image. This revealed that the rocks at the Venera 9 site were not just flat slabs, but had complex, sharp vertical reliefs, confirming their tectonic fracturing. Finally, there is the matter of super-resolution. The original data transmission was limited by the baud rate. The resolution was roughly comparable to a very early webcam, 128 or 252 lines. However, because the scanner moved continuously, the analog signal from the photodetector was sampled at discrete intervals. By analysing the way the signal changed between samples, the slope of the voltage, modern signal processing can infer subpixel details. This technique, combined with the fact that some landers transmitted the same scan twice, if they survived long enough, allows for image stacking. By averaging multiple scans of the same scene, random noise cancels out, while the constant signal of the rock features remains, allowing researchers to sharpen the image beyond the theoretical limit of a single transmission. The legacy of this technical image processing is that the Venus we know is not a static snapshot from 1975 or 1982. It is a dataset that continues to evolve. As our algorithms for noise reduction, color grading, and 3D projection improve, the same magnetic tapes recorded decades ago yield new secrets. We can now see the dust settling on the landing gear. We can distinguish the texture of the soil between the basalt slabs. We can correct the color with a precision that reveals the subtle, mineralogical differences between the landing sites. The images were not merely photographs. They were scientific measurements of brightness and wavelength, encoded in a stream of bits that had to be fought for, protected from the static of the void, and reconstructed with mathematical rigor. The grainy, high-contrast photos in the newspapers were just the surface. The digital reality beneath them was a high-fidelity testament to a world that defies the naked eye, revealed only through the patient application of code to chaos. This processing bridge, the translation of voltage into vision, is what allowed humanity to truly inhabit, if only virtually, the surface of its sister planet. The arrival of these images forced a rewrite of planetary geology textbooks. The swamp theory was dead. The windswept desert theory was dead. Venus was a world of solid rock, shaped by heat and volcanic activity. The lack of significant erosion suggested that the surface was relatively young in geological terms, perhaps only hundreds of millions of years old rather than billions. This led to the terrifying hypothesis that Venus undergoes periodic global resurfacing events, where the entire crust melts or is buried by massive lava flows, resetting the geological clock. The images also provided context for the atmospheric data. Knowing that sunlight reached the surface allowed scientists to refine their models of the greenhouse effect. It wasn't just that heat was trapped, it was that the surface absorbed solar energy and re-radiated it, turning the lower atmosphere into a heat engine. The interaction between the hot rocks and the supercritical carbon dioxide fluid at the surface created a chemical environment unlike anything on Earth, where minerals could be baked out of the ground and transported into the air. For all their clarity, the Venera 9 and 10 images had one major limitation. They were black and white. Scientists could see the texture of the world, but they could not see its true colour. The question of colour was critical for chemical analysis. Iron oxides, for example, would appear red, while sulfur compounds might appear yellow. To solve this, the next generation of landers, Venera 13 and 14, were equipped with colour filters. When Venera 13 landed in 1982, it scanned the surface through red, green and blue filters. The composite image revealed a world bathed in a suffocating deep orange glow. There were no blues or greens. The rocks were orange, the sky was orange, and the horizon was orange. This was not the true colour of the surface materials, but the result of the atmosphere acting as a massive blue-blocking filter. To determine the true colour of the rocks, scientists looked at the colour calibration chart attached to the lander. The white strip on the chart appeared orange in the image, and the blue strip appeared almost black. By mathematically correcting for this atmospheric tint, they determined that the rocks were actually a dark grey, similar to Earth's basalt. But to a human eye standing there, the world would forever be sepia-toned. Venera 13 and 14 represented the apex of the Soviet effort. Launched in 1981, these probes were heavier, smarter, and more robust. Venera 13 survived for a record 127 minutes, transmitting a wealth of data. Beyond the colour cameras, these landers carried a new auditory experiment. A microphone, originally intended to detect seismic thunder, recorded the ambient sound of the planet. The audio revealed a low, constant aerodynamic drone, the sound of the wind. Although the wind speed was low, roughly half a metre per second, the density of the air meant that it pushed against the microphone with significant force. The microphone also captured the sharp, explosive sound of the lander's drill firing into the rock, followed by the grinding of the mechanism. This proved that the dense atmosphere was an excellent conductor of sound, confirming that Venus was a noisy, dynamic environment. The clarity of the Venera 13 panoramas led to one of the most controversial episodes in the program's history. Decades after the mission, Russian scientist Leonid Sanformality analysed the sequence of images and claimed to spot anomalies. He identified a feature he called the scorpion, a structured object that appeared to emerge from the soil, move, and then vanish in subsequent scans. He also noted a black flap that seemed to change position. Sanformality suggested these could be evidence of exotic life forms adapted to the high heat. However, the global scientific community, along with other Russian experts, quickly debunked this. The moving objects were identified as debris from the lander itself, pieces of insulation and plastic covers that melted and detached as the probe heated up. The movement was the result of these materials shifting in the wind or the lander settling into the soil. The scorpion was simply a noise artifact or a piece of the spacecraft. While the biological theory was rejected, the incident highlighted how dynamic the interaction between the machine and the environment truly was. The lander was not sitting in a vacuum. It was slowly disintegrating in a violent chemical bath. With the collapse of the Soviet Union in the early 1990s, the Venera program ended, and the massive archives of data fell into disarray. The original magnetic tapes containing the raw telemetry were stored in conditions that were far from ideal. Over time, the physical media began to degrade, threatening to erase the only record of humanity's contact with the surface of Venus. Much of the data was lost or forgotten, scattered across different institutes. The images that remained in public circulation were often the low-quality, high-contrast versions from the original press releases. It wasn't until the digital age that a concerted effort was made to recover the original signals. This required a form of digital archaeology, finding the old tape drives, reading the decaying magnetic signals, and writing new software to decode formats that had not been used in 40 years. In the 2000s, independent researchers and image processing experts, most notably Don Mitchell, began to work with the recovered raw data. Modern computers could process signal noise much more effectively than the mainframes of the 1980s. They could fill in missing pixels, correct the geometric distortions with higher precision, and balance the contrast to reveal details that had been invisible for decades. This restoration work was a revelation. The new images showed the texture of the soil and the layering of the bedrock with unprecedented clarity. They revealed that the horizon line was further away than previously thought, and they brought out the subtle variations in the rock structures. These restored panoramas are now the definitive record of the surface, stripping away the grain and static of the Cold War era to show the planet as it truly is. While the landers provided the close-up view, they were pinpricks on a massive globe. To understand the planet as a whole, scientists needed to see through the clouds from orbit. The Soviet Venera 15 and 16 missions, followed by NASA's Magellan spacecraft in the 1990s, used synthetic aperture radar to map the entire planet. Radar could pierce the clouds that blocked optical cameras. These missions revealed a surface dominated by volcanism on a global scale. They found massive shield volcanoes, lava channels thousands of kilometers long, and strange circular structures called coronae. The radar maps provided the context for the lander images, showing where those rocky plains fit into the larger tectonic puzzle. However, radar is abstract. It provides a topographic map, not a photograph. It lacks the visceral reality of the optical images returned by the landers. In recent years, our view of Venus has been refined by flybys and orbiters like the European Venus Express and Japan's Akatsuki mission. The Parker Solar Probe, while destined for the Sun, captured stunning images of Venus's night side in the near-infrared spectrum. Surprisingly, the probe's sensors could detect the faint thermal emission of the surface glowing through the clouds. These observations have confirmed that the surface temperature remains constant and that the windows in the atmosphere allow for some infrared remote sensing. This has opened up new possibilities for mapping the surface composition from orbit, looking for active lava flows or hotspots that would indicate the planet is still geologically alive today. The legacy of the Venera program is one of absolute technical triumph. In the history of spaceflight, no other nation has successfully landed a camera on the surface of Venus and returned data. The engineering challenges, the heat, the pressure, the acid, were overcome with a combination of brute force and clever physics that has not been replicated since. The data collected by these probes remains the foundation of all modern Venus science. Every model of the atmosphere, every theory about the surface geology, and every proposal for a future mission is built upon the hard numbers transmitted by those titanium spheres in the 1970s and 80s. The program demonstrated that even the most hellish environments in the solar system are within the reach of human ingenuity. Despite the success of Venera, we have not returned to the surface with a camera since 1982. Proposals for new landers, such as NASA's Da Vinci mission or Russia's proposed Venera D, aim to break this 40-year hiatus. The next generation of surface imaging will likely move beyond the mechanical scanners of the past. Engineers are developing high-temperature electronics based on silicon carbide that can operate at 500 degrees Celsius without cooling. This would allow a lander to survive not for an hour, but for days or even weeks. Such a mission could record the transition from day to night, monitor the weather, and capture high-definition video of the Venusian landscape, finally bringing the morning star into the era of modern digital imaging. We rely today on data collected by a titanium sphere that melted 40 years ago. Until a new lander survives the descent, the yellow rocky plains of the Venera panoramas remain our only true view of this alien world. The success of the Venera program serves as a reminder of what is possible when scientific curiosity is backed by unwavering engineering resolve. The images they returned did not show a world we could inhabit, but they showed a world we could understand. They replaced the myth of the swamp with the reality of the rock, and in doing so they expanded the horizon of human knowledge to the very floor of hell itself. Yet, these static images belie a dynamic and terrifying truth that suggests the planet is fundamentally broken in ways we're only just beginning to grasp. When we stare at the yellowed, distorted horizons captured by Venera, we are looking at a crime scene where the culprit has long since fled, leaving behind a victim that has been mutilated beyond recognition. The realization that something is seriously off with Venus goes deeper than the surface temperatures or the crushing pressure. It strikes at the very heart of planetary formation theories. According to the standard models of stellar accretion, Venus and Earth should be siblings not just in size and composition, but in history and habitability. They formed in the same neighborhood of the solar nebula, sweeping up the same silicates and metals, and were bombarded by the same icy comets delivering water. By all rights, Venus should be a tropical version of Earth, perhaps a bit warmer, but teeming with oceans and potentially life. Instead, it is the solar system's cautionary tale, a planet that took a wrong turn at a critical juncture in deep time. The first indication that the planet is behaving incorrectly lies in its rotation. If you were to stand on those basaltic plains shielded from the heat, you would witness a sun that rises in the west and sets in the east, a motion that defies the angular momentum inherited from the birth of the solar system. This retrograde rotation is agonizingly slow, with a single sidereal rotation taking 243 Earth days, which is longer than the Venusian year itself. This means that on Venus, a day lasts longer than a year. The prevailing theory suggests that a massive protoplanetary impactor, distinct from the one that created Earth's moon, struck Venus with such force that it not only halted the planet's spin, but reversed it entirely. However, unlike Earth, which gained a stabilizing moon from its collision, Venus was left solitary and wobbling. This slow rotation has catastrophic consequences for the planet's internal dynamo. Without the rapid spin to churn the molten metal in its core, Venus fails to generate a global magnetic field. It stands naked before the solar wind, stripped of the protective shield that allows Earth to retain its atmosphere and oceans against the stripping power of the Sun. This lack of a magnetic field connects directly to the mystery of the water. We know through the analysis of the deuterium to hydrogen ratio in the Venusian atmosphere that the planet once possessed vast reserves of water. Deuterium, a heavier isotope of hydrogen, is less likely to escape into space when water molecules are broken apart by solar radiation. The high concentration of deuterium remaining in the atmosphere today is the chemical fingerprint of a lost ocean, a ghostly echo of a world that might have looked strikingly like our own for the first 2 billion years of its existence. The tragedy of Venus is not that it was born dead, but that it was likely alive and habitable for eons before the climate tipped. The mechanism of this death was a runaway greenhouse effect, a feedback loop where rising temperatures evaporated the oceans, adding water vapour to the atmosphere, which trapped more heat, which evaporated more water, until the oceans were entirely boiled away. Once the water was in the upper atmosphere, ultraviolet light dissociated the molecules, and the solar wind, unchecked by a magnetic field, stripped the hydrogen away, losing the water to space forever and leaving behind a desiccated husk choked by carbon dioxide. However, the surface geology presents an even more disturbing puzzle that the Venera images hint at but cannot fully explain. When radar mappers like Magellan stripped away the clouds digitally, they revealed a surface that was statistically too young. On a planet as old as the solar system, we expect to see a landscape scarred by billions of years of impact craters, like the highlands of the Moon or the plains of Mars. Venus, however, has a sparse and random distribution of craters, suggesting that the entire surface is roughly the same age, somewhere between 300 and 600 million years old. This implies that Venus does not resurface itself gradually through plate tectonics like Earth. Instead, it appears to undergo catastrophic global resurfacing events. The pressure builds up within the mantle, unable to escape through steady volcanic vents or shifting plates until the entire crust becomes unstable. In a geologic heartbeat, the planet effectively turns itself inside out, flooding the entire globe with magma and erasing all history of what came before. We are looking at a planet that suffers from periodic global heart attacks, resetting its surface and potentially releasing massive pulses of carbon dioxide that maintain its hellish climate. The atmosphere itself, the very blanket that suffocates the planet, behaves with a distinct and inexplicable autonomy. While the solid planet rotates at a glacial pace, the atmosphere whips around the surface at incredible speeds, a phenomenon known as superrotation. Winds in the upper cloud decks reach speeds of 360 kilometers per hour, circling the planet in just 4 Earth days. This atmospheric engine transports heat from the day side to the night side so efficiently that there is virtually no temperature difference between noon and midnight. But within these clouds, there are anomalies that suggest complex chemistry, or perhaps something more controversial. Since the early days of telescopic observation, astronomers have noticed dark patches in the Venusian clouds that absorb ultraviolet light. These unknown UV absorbers fluctuate in contrast and distribution over time, behaving remarkably like blooms of algae in Earth's oceans. They exist at an altitude where temperatures and pressures are relatively mild, leading to the tenacious, albeit speculative, hypothesis that while the surface of Venus is dead, the clouds might be a refuge for microbial life that migrated upward as the oceans boiled below. This hypothesis gained sudden and volatile traction with the detection of phosphine gas in the cloud decks. On Earth, phosphine is produced almost exclusively by industrial processes or by anaerobic microbes living in oxygen-starved environments. Its presence in the Venusian atmosphere, if confirmed, lacks a known abiotic explanation that fits the current models of Venusian chemistry. While the initial euphoria has been tempered by subsequent reanalysis and debate over the signal's validity, The mere possibility forces us to reconsider the definition of the habitable zone. We have spent decades looking for life on surfaces, digging into the Martian regolith, or cracking the ice of Europa. But Venus challenges us to look at the atmosphere as a biosphere. If life can persist in the hyperacidic, sulfur-rich clouds of a runaway greenhouse world, it implies that life is far more resilient and ubiquitous than we dared to imagine. It suggests that the universe might be teeming with life, but not necessarily on the pleasant blue marbles we tend to look for. The urgency to return to Venus is driven by the need to resolve these contradictions. The static images from the Soviet era are no longer enough. We need dynamic data. We need to understand the precise isotopic composition of the noble gases to determine when and how the atmosphere formed. We need to measure the seismic activity to see if the planet's heart is still beating, or if it is building up to another catastrophic resurfacing. The proposed missions of the coming decade, utilizing radar that can peer through the clouds with unprecedented resolution, and probes that can taste the atmosphere as they descend, are designed to treat Venus not just as a planetary destination, but as a forensic investigation. We are trying to solve the murder of a habitable world, and the clues are hidden in the isotopic ratios of the atmosphere and the mineralogy of the highlands. Furthermore, the study of Venus is a study of our own potential future. The planet serves as a dark mirror to Earth, a demonstration of the fragility of planetary climate systems. The difference between the lush biosphere of Earth and the sterile inferno of Venus is a matter of atmospheric composition and feedback loops. As we grapple with anthropogenic climate change on our own world, Venus stands as the ultimate laboratory for greenhouse physics. It shows us the endpoint of a climate system pushed beyond its tipping point. While Earth is not in danger of becoming Venus anytime soon, the underlying physics are identical. Understanding how Venus lost its way is crucial for understanding the stability of our own biosphere. The lessons from Venus are not merely academic, they're existential. The planet teaches us that habitability is not a permanent state, but a delicate equilibrium that can be destroyed by geological or astronomical accidents. There is also the question of the tesserae, the oldest terrain on Venus, which the Venera landers did not visit. These highly deformed, rugged regions appear to be the ancient continental crust that survived the global resurfacing. If we could land a probe there, we might find granite, a rock type that requires liquid water to form. Finding granite on Venus would be the smoking gun, irrefutable proof that this burning world was once a pale blue dot with continents and oceans. It would confirm that Earth and Venus were indeed twins, separated by a tragic divergence in their evolutionary paths. The Venera panoramas show us the basaltic plains, the lava fields that covered the past, but the highlands might still hold the fossilized remains of the Venus that used to be. The technological leap required to explore these mysteries is immense. To survive longer than the mere hours achieved by the Venera landers, we are developing electronics based on silicon carbide rather than standard silicon. These high-temperature chips can function at 500 degrees Celsius without bulky cooling systems, theoretically allowing a lander to operate on the surface for weeks or months. Imagine a mission that could transmit a continuous live stream from the surface of Venus, watching the shadows shift as the sun crawls across the sky, listening to the acoustic signature of the wind, and monitoring the chemical weather in real time. Such a mission would transform Venus from a static, historical curiosity into a dynamic, monitored world. We could watch the weather patterns of a runaway greenhouse effect in action, providing data that would refine our climate models back on Earth to an unprecedented degree of accuracy. We must also consider the philosophical implications of the visuals themselves. The Venera images are haunting because they are so familiar yet so alien. The flat rocks, the dirt, the horizon. It looks like a desert on Earth, perhaps a desolate stretch of Nevada or the volcanic fields of Iceland. It does not look like a sci-fi alien world with purple trees or floating mountains. It looks like a place we could walk, were it not for the fact that the air is fire and the pressure is crushing. This banality is what makes the horror of Venus so potent. It is a terrestrial landscape composed of the same basalt and dust, but raised to conditions that are incompatible with the structure of biological matter as we know it. It creates a cognitive dissonance, a rejection of the idea that a place so physically similar to Earth could be so hostile. It reminds us that the parameters for life are narrow and that the universe is largely indifferent to our biological requirements. As we analyse the sharp, slab-like rocks in the Venera 13 and 14 images, we must remember that these rocks are interacting with the atmosphere in ways that rocks on Earth do not. At these temperatures, the chemistry of the surface is hyperactive. Minerals are constantly reacting with the supercritical carbon dioxide and sulfur compounds, growing crystals or eroding at rates that would be visible to a long-duration lander. The surface of Venus is not just sitting there, it is cooking. The metallic snow that coats the mountain peaks, likely lead sulfide or bismuth telluride that condenses out of the atmosphere at high altitudes, is another example of this alien weather cycle. On Venus, it snows heavy metals. This is a planet where the mountains are capped not with water ice, but with frost made of semiconductors. The mystery of the unknown is what drives the obsession with these images. Every pixel of the Venera panoramas has been scrutinized for decades, subjected to modern image processing techniques to squeeze out every drop of information. We have corrected the color, removed the noise, and reprojected the perspective to create a human view. Yet, we are still looking at data from the early 1980s. The fact that we have not returned to the surface with a camera in nearly half a century is a gap in our exploration of the solar system that borders on negligence. We have sent fleets of rovers to Mars, orbiters to Saturn and Jupiter, and even a probe to Pluto, yet our closest neighbour, the planet that can teach us the most about the fate of Earth-like worlds, remains largely unvisited by modern surface assets. This neglect is partially due to the difficulty. Mars is easy. You can drive around for a decade. Venus kills your robot in an hour. But it is also due to the narrative that Venus is a solved dead end. The Venera images, in their stark finality, contributed to this feeling. They showed a dead rock, and the world moved on to the search for water on Mars. But the something seriously off with Venus is exactly why we must go back. The anomalies in the atmosphere, the youth of the surface, the lack of a magnetic field, and the potential for ancient habitability make it the most scientifically critical destination in the inner solar system. We need to understand why a planet that looks like Earth, is the size of Earth, and is made of the same stuff as Earth, turned into a pressure cooker. The next generation of explorers will not just be looking for rocks, they will be looking for the timeline of the catastrophe. By drilling into the surface, even just a few centimeters, a modern lander could analyze the mineral oxidation states to determine how long the surface has been exposed to the current atmosphere. This would help constrain the date of the global resurfacing event. Was it a rapid, cataclysmic turnover that happened in a few thousand years, or a slow burn that lasted millions? The answer changes our understanding of planetary geophysics. If a planet can suddenly melt its entire surface, we need to know if that is a common phase in planetary evolution, or a freak accident specific to Venus. Moreover, the exploration of Venus challenges our engineering capabilities in a way that Mars does not. Designing a rover for Venus requires mechanical computers, wind-powered movement, or high-temperature electronics that border on steampunk technology. It forces us to rethink how we build machines. We cannot rely on the delicate microchips that power our lives on Earth. We have to build tanks that can think. This engineering challenge is a lesson in itself, pushing the boundaries of material science and robotics into regimes that have applications here on Earth, from monitoring inside jet engines to exploring deep geothermal vents. The story of Venus is far from over. The grainy yellow photos from the Soviet Union are the prologue, not the conclusion. They are the initial reconnaissance of a world that is hiding its secrets behind a veil of acid and heat. As we stand on the precipice of a new era of Venusian exploration, with missions from NASA and ESA on the horizon, we must be prepared for the possibility that the reality of Venus is even stranger than the images suggest. We might find that the planet is still geologically active today, with volcanoes erupting right now beneath the clouds. We might find that the atmosphere is a complex ecosystem of chemical, if not biological, activity. We might find that Venus is not a dead planet, but a dormant one, or perhaps a planet living a life so radically different from Earth's that we have failed to recognize it. In the end, the images from Venera show us a world that is off because it challenges our Earth-centric bias. We want planets to be like ours, and when they are not, we dismiss them as dead. But Venus is a vibrant, violent, and dynamic world that demands to be understood on its own terms. It is a reminder that the universe is under no obligation to be habitable, and that the peace and stability of our own blue marble is a rare and precious anomaly in a cosmos of fire and ice. The lesson of Venus is one of humility. It teaches us that we are lucky to be here, and that we must never take the stability of our own world for granted. The floor of hell is real, it is next door, and it is waiting for us to return and learn its secrets. High above the crushing pressure and the lead-melting temperatures of the surface, the Venusian atmosphere presents a mystery that is perhaps even more disturbing than the hellscape below. When astronomers first turned their ultraviolet telescopes toward the planet in the mid-20th century, they expected to see a featureless white billiard ball shrouded in a uniform layer of sulfuric acid clouds. Instead, they found the planet marked by vast, shifting dark patches. These dark regions absorb nearly half of the solar energy the planet receives, driving the ferocious superrotation of the atmosphere. Yet after decades of study, we still do not know what they are. This is the unknown ultraviolet absorber, a substance that defies identification and behaves with a strange, almost organic unpredictability. The material exists in the upper cloud decks, right where the temperature and pressure are surprisingly similar to those on Earth, leading to the unsettling hypothesis that these dark patches are not mineral dust or sulfur allotropes, but colonies of microorganisms suspended in the sky. The behavior of these dark patches adds weight to the unease scientists feel when analyzing the data. They do not mix uniformly as an inert gas would. Instead, they change contrast and distribution over timescales of days to years, expanding and contracting in patterns that resemble the algae blooms found in Earth's oceans. The correlation is purely visual, yet the persistence of the mystery forces us to confront the limitations of our remote sensing capabilities. If the absorber is indeed sulfur chloride or some form of ferric chloride, the chemical models suggest it should be unstable and short-lived, reacting quickly with the surrounding atmosphere to become transparent. The fact that it remains persistent, replenishing itself constantly against the chemical gradient, suggests a source of production that we have yet to locate. The atmosphere of Venus is seemingly out of equilibrium, maintaining a chemical state that should naturally collapse, which is exactly the kind of thermodynamic signature usually associated with biological processes. This atmospheric anomaly links directly to the phenomenon of superrotation, another aspect of Venus that indicates something is fundamentally incorrect in our standard planetary models. On Earth, the atmosphere moves roughly at the speed of the planet's rotation, driven by the friction of the ground. On Venus, the solid planet rotates with agonizing slowness, taking 243 Earth days to complete a single turn, spinning backward in a retrograde motion. However, the atmosphere ignores this sluggish pace entirely. The cloud tops whip around the planet at speeds exceeding 300 kilometers per hour, circling the entire globe in just 4 Earth days. This means the atmosphere is moving 60 times faster than the surface it sits upon. According to fluid dynamics and angular momentum conservation, this should be impossible without a constant massive injection of energy to maintain the speed against frictional losses. The unknown UV absorber is likely the engine of this speed, trapping solar heat and converting it into kinetic energy. But the efficiency of this engine is terrifyingly high, suggesting that the Venusian climate system operates on physics we have yet to fully replicate in our simulations. The sense that Venus is hiding a biological secret deepened significantly with the detection of phosphine gas in the cloud decks. Under the crushing gravity and oxidizing chemistry of Venus, phosphorus should exist as phosphates, bound to oxygen. Phosphine, which consists of a phosphorus atom bonded to 3 hydrogen atoms, is a molecule that requires a tremendous amount of energy to create in such an environment. On Earth, phosphine is produced exclusively by industrial factories or by anaerobic bacteria living in oxygen-starved environments like swamps or the guts of animals. It is a distinct biosignature. When radio telescopes detected the spectral fingerprint of phosphine in the Venusian clouds, it sent a shockwave through the planetary science community because there is no known geological or photochemical pathway to produce it in the quantities observed. The presence of this gas implies that the atmosphere is being actively pushed away from chemical equilibrium. To maintain the observed levels of phosphine, something must be producing it constantly to offset the rate at which it is destroyed by sunlight and sulfuric acid. If that source is not biological, then Venus hosts a form of photochemistry or volcanism completely unknown to science. The implications are stark. Either we have discovered the first signs of extraterrestrial life, floating in the acid clouds of our nearest neighbour, or our understanding of rocky planet chemistry is fundamentally flawed. The debate that followed the discovery was fierce, with reanalyses of the data questioning the signal's strength. Yet independent confirmations continue to suggest that something anomalous is happening in those clouds. The signal appears to vary over time, much like the UV absorber, pulsing in a rhythm that could imply a seasonal cycle or a blooming event. This potential biosphere would exist in a precarious habitable zone, a narrow strip of atmosphere sandwiched between the freezing vacuum of space and the incinerating oven of the surface. If life exists here, it is a remnant of a lost age, the last survivors of a biosphere that was forced to migrate upward as the planet's oceans boiled away billions of years ago. This concept reframes Venus not as a sterile wasteland, but as a dying world holding on to its last breath of life in the only sanctuary remaining. It transforms the image of the planet from a geological curiosity into a tragic biological refuge, where organisms must cycle endlessly within the droplets of sulfuric acid, never touching the ground, evolving to survive in a medium that would dissolve human flesh in seconds. Descending from the clouds to the solid crust, the sense of wrongness shifts from chemical to geological. When the Magellan spacecraft mapped the surface of Venus with radar in the early 1990s, scientists expected to see a surface battered by billions of years of asteroid impacts similar to the Moon, Mars, or Mercury. Craters are the clock by which we tell the age of a planetary surface. The more craters, the older the terrain. Instead, Magellan revealed a startlingly young surface. There are fewer than 1,000 impact craters on the entire planet, and they are randomly distributed, showing no clustering or degradation patterns. This distribution implies that the entire surface of Venus is roughly the same age, estimated to be between 300 and 600 million years old. This uniformity presents a catastrophic narrative known as the global resurfacing event. It suggests that for billions of years, Venus builds up internal heat that cannot escape, because the planet lacks the continuous release valve of plate tectonics. On Earth, the motion of crustal plates constantly recycles the surface and releases internal heat through mid-ocean ridges and volcanoes. Venus, having a single, locked lithospheric shell, bottles this heat up until the mantle temperature reaches a critical threshold. At that point, the entire crust becomes unstable. The solid rock weakens, catastrophic melting occurs on a planetary scale, and the entire surface founders and sinks into the mantle, to be replaced by a fresh ocean of lava that eventually cools into a new crust. If this theory is correct, it means Venus is a planet that breathes in apocalyptic cycles. It spends hundreds of millions of years in a quiescent state, accumulating stress and heat, only to destroy itself and start over in a violent paroxysm that erases all history. The surface we see today is merely the aftermath of the most recent reset. This challenges the uniformitarian view of geology, which favours slow, steady change. Venus demands a catastrophist interpretation. It suggests that the planet is currently in a dormant phase, a lodgement period where the crust is thickening and the heat is building again, ticking down toward the next global immolation. The randomness of the craters indicates that since the last resurfacing, the planet has been largely dead geologically, preserving the scars of impacts perfectly in the pristine lava plains until the next great overturning wipes the slate clean. However, not all of Venus fits this model of a young uniform surface, and the exceptions are where the true strangeness lies. Standing in stark contrast to the vast, smooth volcanic plains are regions known as tesserae. These are areas of incredibly complex, highly deformed terrain that look like crumpled tinfoil from orbit. The tesserae are lighter in colour and reflect radar brightly, indicating a rough, fractured texture. They appear to be the oldest rocks on the planet, islands of ancient crust that somehow survived the global resurfacing event. They are twisted, folded, and faulted in every direction, suggesting a history of intense tectonic activity that does not match the stagnant lid model currently applied to the planet. The existence of tesserae implies that Venus once had a very different geological regime, perhaps even one resembling Earth's plate tectonics. Some planetary geologists hypothesize that these are the remnants of ancient continents, composed of granitic rocks that formed in the presence of water. On Earth, granite is formed when water-rich crust is subducted and melted. It is a rock type inextricably linked to oceans and tectonics. If the tesserae are indeed made of granite, It provides physical proof that Venus was once a wet, dynamic world, with oceans and moving continents before the greenhouse effect took hold. They are the fossilized skeletons of a dead version of the planet, protruding through the younger basaltic floods like tombstones. The offness here is the preservation of these features. If the global resurfacing event was truly global, the tesserae should have been destroyed or buried. Their survival suggests that the resurfacing was not total, or that the tesserae are buoyant enough to float atop the global magma ocean. Furthermore, recent infrared emissivity data from the Venus Express orbiter suggests that the tesserae radiate heat differently than the surrounding plains, consistent with felsic, continental-style rocks. This data supports the haunting idea that we are looking at the ruins of an Earth-like world, preserved in a distorted, mummified state. The tesserae are the only witnesses to the time before the catastrophe, and their chaotic, fractured nature tells a story of a violent transition from a habitable world to the oven we see today. Deep inside the planet, another anomaly lurks, one that is invisible to the eye but critical to the mystery of Venus. Despite being nearly the same size and density as Earth, and presumably having a similar iron-nickel core, Venus has no internal magnetic field. Earth's magnetic field is generated by the geodynamo, the churning motion of molten iron in the outer core, driven by the planet's rotation and the release of heat. This field protects our atmosphere from being stripped away by the solar wind. Venus, however, is naked in the solar wind. The lack of a magnetic field is baffling because the planet should have plenty of internal heat to drive a dynamo. The absence of a magnetic field is often attributed to the planet's slow rotation, but calculations show that even Venus's sluggish spin should be sufficient to generate a field if convection were occurring in the core. The real culprit appears to be the lack of plate tectonics and the thermal state of the core itself. On Earth, the cooling of the core is aided by the cold slabs of crust sinking into the mantle, which keeps the temperature difference high enough to drive convection. On Venus, the stagnant lid of the crust acts as an insulating blanket, trapping heat in the mantle. This might mean that the core is not cooling fast enough to churn, or that the entire core has become stratified and stable. This lack of a magnetic field has had dire consequences for the planet's history. Without a shield, the solar wind has been interacting directly with the upper atmosphere for billions of years, systematically stripping away the lighter elements. This process is particularly efficient at removing hydrogen. When water molecules in the upper atmosphere are broken apart by ultraviolet light, the hydrogen atoms are light enough to be knocked into space by the solar wind, while the heavier oxygen remains. This mechanism explains why Venus is so dry today. The ratio of deuterium, heavy hydrogen, to normal hydrogen in the Venusian atmosphere is roughly 150 times higher than on Earth. This high DH ratio is a smoking gun, a chemical fossil proving that Venus once had a massive amount of water, likely a global ocean, which was slowly bled into space because the planet's heart stopped beating. The death of the magnetic field was the death knell for the planet's habitability. The physical properties of the Venusian surface rock under current conditions present a rheological nightmare for geologists trying to understand the landforms. At 470 degrees Celsius, basaltic rock behaves very differently than it does on Earth. It becomes more ductile, more prone to deformation, and less able to support high, steep topography over long timescales. Yet we see the Maxwell Montes, a mountain range rising 11 kilometers above the mean planetary radius, higher than Mount Everest relative to sea level. For these mountains to exist without slumping under their own weight in the intense heat, the crust must be exceptionally strong or supported by a dynamic force from below. This contradicts the idea of a hot, soft crust. To explain the mountains, some models propose that the moisture-free nature of the rocks makes them harder. On Earth, water acts as a lubricant within the crystal lattice of minerals, weakening rocks and lowering their melting points. The bone-dry rocks of Venus might be incredibly stiff and brittle despite the temperature, allowing them to support massive loads. However, this stiffness makes the presence of certain volcanic features, like the pancakes, even more puzzling. Pancake domes are steep-sided, flat-topped volcanoes that look like giant viscous discs. They are formed by lava that is extremely thick and pasty. If the crust is dry and the lava is hot, the viscosity should be low, and the lava should run like water, creating flat plains. The existence of these domes suggests a type of evolved, silica-rich magma that shouldn't be common on a planet without water to process the crust. Furthermore, we see features called ticks, volcanic constructs with a central caldera and radiating ridges that look like the legs of a parasite. These are thought to be degraded domes where the flanks have collapsed. The sheer variety of volcanic edifices, from shields to domes to ticks to vast channels called canali that run for thousands of kilometers, indicates a complex magmatic plumbing system that we do not fully understand. The canali are particularly strange. Some are longer than the Nile River but maintain a nearly constant width, implying a lava that flowed freely for months or years without cooling or solidifying, cutting a thermal erosion channel into the rock. This requires a lava composition that is exotic, perhaps carbonatite or sulfur-rich, flowing like river water across a landscape of solid iron. In recent years, the Venus Express mission provided data that challenged the dead planet hypothesis even further. By monitoring the thermal emission from the surface in the near-infrared windows that can penetrate the clouds, scientists detected transient hotspots. In the Ganaki-Chasma Rift zone, distinct spikes in surface temperature were observed, appearing and vanishing over the course of days. These were not subtle variations. They were significant thermal releases consistent with active lava flows breaking out onto the surface. This observational evidence suggests that Venus is not merely a dormant world waiting for the next global resurfacing, but a planet that is volcanically active right now. It is alive in the geological sense. The something off is that we have failed to see the plumes despite this activity. If volcanoes are erupting, they should be injecting sulfur dioxide into the atmosphere, causing spikes in the gas concentration. We have seen these spikes in the historical data from the Pioneer Venus orbiter in the late 1970s and again in the 2000s, but connecting them definitively to specific eruptions has been elusive. The atmosphere effectively masks the surface activity, acting as a thick curtain that blurs the thermal signals. The presence of active volcanism complicates the cratering record. If the planet is resurfacing itself, piecemeal through constant small eruptions rather than one giant cataclysm, then the random distribution of craters becomes harder to explain. A piecemeal resurfacing should leave patches of old and new terrain with varying crater densities, but we see a mostly uniform distribution. This forces a reconsideration of how cratering works on Venus. The thick atmosphere crushes small asteroids before they hit the ground, acting as a filter. Only the big impactors get through. This filter effect might distort the age estimates, making the surface appear younger or more uniform than it actually is. The interplay between the atmospheric shield and the geological engine creates a data set that is intrinsically biased, hiding the true rhythm of the planet's heartbeat. Among the most inexplicable features on Venus are the Baltis Vallis and other similar channels, known as canali. Baltis Vallis is a meandering channel that stretches for nearly 6,800 kilometers, making it longer than any river on Earth. What makes it off is its morphology. Rivers on Earth widen as they flow downstream, fed by tributaries. Baltis Vallis maintains a remarkably constant width of about 1 to 3 kilometers for its entire length. It twists and turns like a river, with meanders and oxbow-like cutoffs, but it was carved by liquid rock, not water. The physics required to keep lava liquid for nearly 7,000 kilometers are staggering. On Earth, lava flows cool and crust over relatively quickly. Even large flood basalts do not form such disciplined river-like channels over such vast distances. To carve Baltis Vallis, the lava must have been extremely hot, extremely low viscosity, and flowing at a high rate for a very long time. It suggests a material closer to the consistency of motor oil or water than typical basalt. Some scientists have proposed that these channels were carved by carbonatite lavas, molten calcium carbonate, which melt at lower temperatures and flow very easily. Others suggest sulfur-rich lavas. The existence of these channels implies a time in Venusian history when the surface conditions allowed for this exotic cryovolcanism or high-temperature erosion. It speaks to a surface environment that was radically different, or a mantle chemistry that is fundamentally alien to our experience. The channel often flows uphill and downhill in the current topography, which indicates that the terrain has warped and buckled after the channel was carved. This deformation confirms that the surface of Venus is not static. It is warping and shifting, destroying the ancient drainage patterns of these lava rivers. The canali are scars of a fluid dynamic event that has no parallel in the solar system, a testament to a time when the planet bled a fluid we cannot identify across a continent-sized distance. High in the northern hemisphere lies Ishtar Terra, a continent-sized highland that hosts the massive Maxwell Montes. Ishtar Terra is unique because it is bordered by steep scarps, cliffs that rise kilometers into the sky from the surrounding plains. The formation of such a high plateau requires immense compressive forces. On Earth, the Himalayas are formed by the collision of India and Asia. There is no evidence of drifting plates on Venus, so the origin of Ishtar Terra is a major problem for planetary scientists. The off aspect of Ishtar Terra is its sheer gravitational presence. It is a massive load on the crust. Without the roots of a mountain belt like those on Earth, where the crust thickens downward into the mantle to support the height, Ishtar Terra should sink. Gravity data suggests that there is indeed some form of support, but whether it is a thermal plume pushing up from below or a strong, thick crust holding it up is unknown. The steepness of the slopes is particularly baffling. In the intense heat of Venus, rock slopes should relax and spread out over millions of years. The fact that the scarps of Ishtar Terra remain sharp and steep implies that they are either very young, formed recently by some violent crustal shortening, or the rock is behaving in a way that defies our rheological models. Furthermore, the surface of Ishtar Terra shows signs of snow. In the radar images, the highest peaks of Maxwell Montes reflect radar waves with brilliant intensity. This is not water snow, which would vaporize instantly. It is metallic snow. The leading theory is that at these high altitudes the temperature drops slightly, allowing vaporized semi-metals like tellurium or lead sulfide, galena, to condense out of the atmosphere and coat the mountain peaks. Imagine a mountain range where the frost is made of lead and the drifts are composed of semiconductors. This metallic capping is a stark reminder of the alien chemistry at play, where the phase changes of heavy metals replace the water cycle of Earth. At the surface of Venus, the atmosphere is not a gas in the way we understand it. At 92 bars of pressure and roughly 740 Kelvin, carbon dioxide enters a state known as a supercritical fluid. It is no longer a gas, nor is it a liquid. It possesses properties of both. It has the density of a liquid, but expands to fill its container like a gas. This means that walking on the surface of Venus would not feel like walking through air. It would feel like walking through a deep ocean of compressed hot fluid. This supercritical nature changes everything about how the surface evolves. The wind speeds at the surface are low, barely a meter per second, but because the air is so dense, a gentle breeze on Venus hits with the force of a rushing river. It can roll boulders and scour bedrock. The transport of dust and sand in this medium is highly efficient. The images from the Venera landers showed slab-like rocks with little dust, but we know dust exists. The supercritical CO2 likely acts as a powerful erosional agent, smoothing out rough edges and transporting material into low-lying areas, creating a sedimentary process that mimics water deposition on Earth. The heat transfer properties of a supercritical fluid are also immense. This fluid wraps the planet in a blanket that conducts heat with terrifying efficiency, ensuring that there is no relief from the temperature anywhere. The night side is just as hot as the day side, the poles are just as hot as the equator. There is no escape. This homogenization of temperature is part of what makes the planet so off. Most planets have temperature gradients. Venus is a monochromatic oven. This state creates a sensory environment that is difficult for humans to conceive. A world where the air itself is a solvent, a heavy, crushing ocean of carbon that dissolves the distinction between atmosphere and ocean. Returning to the specific images that sparked the controversy, we must look closely at the Venera 13 panoramas. While the scorpion of Venera 13 is often dismissed as a lens cap or noise, the black flap seen in the images is harder to explain away. In the sequence of images taken over time, an object appears to change shape or position. The official explanation is that the lander, settling into the soft soil or shifting due to thermal expansion, caused the perspective to change or debris to move, but the appearance of the object is distinct against the regolith. What is truly off in the Venera 13 images is the texture of the soil itself. It appears layered, almost sedimentary. In a volcanic world, we expect basalt flows, jagged rocks, or ash. The presence of thin, platy layering suggests a depositional process. Could this be ash settled from the air? Or is it evidence of the supercritical fluid erosion mentioned earlier? The soil mechanics inferred from the impact of the lander suggest a material that is porous but brittle, crushing easily under the metal ring of the spacecraft. There is also the colour. The raw images are orange-tinted due to the thick atmosphere filtering the sunlight, blocking all blue light. But when colour-corrected to show what the rocks would look like under white light, they appear dark grey, typical of basalt. However, the weathering patterns are strange. The rocks are sharp and angular, yet the environment is supposedly highly erosive chemically. If the atmosphere is so corrosive, why are the rocks not rounded and smooth? The persistence of sharp features suggests that either the rocks are very young, supporting the active volcanism theory, or the chemical erosion rates are slower than predicted, perhaps because the surface is so dry that the acid cannot attack the rock effectively. The ultimate wrongness of Venus is its role as a mirror to Earth. We look at Venus and see a twin that went down a dark path. The isotopic evidence of lost water, the carbon-choked atmosphere, and the surface temperature all point to a runaway greenhouse effect. This is a process where a planet gets slightly too hot, causing water to evaporate. Water vapor is a potent greenhouse gas, so it traps more heat, causing more evaporation in a vicious feedback loop. Eventually, the oceans boil, the carbonate rocks release their CO2, and the planet is sterilized. Venus shows us that habitability is not a permanent state. It is a fragile equilibrium. The off feeling one gets when studying Venus is the realization that the difference between a garden and a furnace is merely a matter of a few degrees of insulation and a few feedback loops. Venus likely started with oceans. It may have had blue skies and rain. It may have had life. And then, through a slight shift in solar luminosity or a massive volcanic event, it tipped over the edge. The current state of Venus is a stable hell. It has been this way for hundreds of millions of years. This stability is mocking. It suggests that the natural state of a rocky planet with an atmosphere in our solar system's habitable zone might actually be a Venus-like state. And Earth is the lucky anomaly that has managed to stave off the heat death through a biological thermostat. The images of the Venusian surface are not just pictures of a distant world. They are potential pictures of Earth's distant future. To truly understand what is off with Venus, we must go back. Orbital data is not enough. We need to touch the surface again. The upcoming missions like NASA's Da Vinci Plus and Veritas and ESA's Envision are designed to crack the shell of this mystery. Da Vinci Plus will drop a probe through the atmosphere, sampling the chemistry of the clouds and the lower atmosphere in unprecedented detail. It will sniff for noble gases that can tell us the history of the water loss. It will look for the phosphine. It will take high-resolution descent images of the tesserae, finally showing us what the continents look like up close. Veritas will map the surface with a new generation of radar, peering through the clouds to see if the volcanoes are moving, if the crust is shifting, and if the black patches in the atmosphere correlate with surface features. These missions are not just scientific inquiries, they are forensic investigations. We're returning to the scene of a planetary crime to find out who killed Venus. Was it the sun? Was it the volcanoes? Or was it something intrinsic to the planet's formation? Until we have those answers, the images from Venera remain our only true window into this alien reality. They stand as grainy, distorted testaments to human ingenuity and the sheer strangeness of the cosmos. They show a world that is familiar yet deeply wrong, a landscape that mimics Earth but is composed of the stuff of nightmares. There's something off is the cognitive dissonance of seeing a horizon that looks like a desert on Earth, while knowing that the air is poison, the sky is acid, and the ground is glowing with the heat of a kiln. If the phosphine signal is confirmed, and if the UV absorber turns out to be biological, the implications for the universe are staggering. It would mean that life is not fragile. It would mean that life is tenacious, adaptable, and capable of surviving in the most hostile environments imaginable. It would mean that the Goldilocks zone is a myth, and that life can thrive in the fires of hell just as well as in the cool waters of Earth. This would fundamentally change our search for extraterrestrial intelligence. If Venus, the most off planet we know, can harbour life, then the universe must be teeming with it. It would mean that we're not looking for Earth 2.0, we should be looking for any place where energy flows. The dark patches of Venus might be the largest colonies of life in the solar system by biomass, floating serenely above a dead world. This possibility transforms the offness of Venus from a warning into a promise. It suggests that even when a world dies, life finds a way. It retreats to the clouds, it changes its chemistry, it endures. The image of the barren rocks of Venera is then not a picture of death, but a picture of a basement, while the house above is full of strange floating ghosts. The serious issue with the planet is not that it is dead, but that it is hiding its life where we didn't think to look. Ultimately, the rocks of Venus remain silent. The Venera landers survived for only an hour or two before succumbing to the heat. We have mere minutes of data from the surface. This scarcity of information amplifies the mystery. We project our fears and our theories onto those grainy pixels. We see scorpions where there are rocks. We see cities where there are lava flows. But the reality is likely far stranger than our pareidolia. The rocks shown in the Venera images are sharp, pletty, and scattered. They sit on a bed of dark soil. The horizon is a blur of yellow light. There is no blue, no green, no movement other than the shimmering of heat haze. It is a stillness that feels heavy. The pressure is so high that sound would travel differently, faster and deeper. A human voice on Venus would sound distorted, a deep growl. The environment is alien in every sensory modality. The fact that we have these images at all is a miracle. They were transmitted by analog radio signals across millions of kilometers, from a machine cooking to death. They are the last will and testament of the Soviet space program's robotic emissaries. And in those pixels, we see the offness staring back at us. It is the face of a planet that went wrong, a sibling that grew up twisted and angry. It is a reminder that the cosmos is indifferent to our comfort, and that the beautiful blue stability of Earth is a delicate exception in a violent universe. The floor of hell is indeed real, and it is waiting for us to return, not to conquer it, but to understand why it exists, and to ensure that our own world does not follow in its burning footsteps. To look closely at the panoramas returned by Venera 13 and Venera 14 is to engage in a kind of visual archaeology that borders on madness. When we scrutinize the raw data, stripped of the smoothing algorithms and artistic interpretations that often grace popular science magazines, we find details that defy easy explanation. The surface of Venus does not merely look dead, it looks suspended in a state of impossible tension. The rocks visible in the Venera 14 panorama, for instance, present a geological contradiction that has puzzled planetary scientists for decades. We see layered plate-like structures, stratified slabs that resemble sedimentary rocks on Earth. On our planet, such formations are typically born from the gentle deposition of silt in water or the accumulation of wind-blown sand over eons. Yet on Venus, there is no water, and the surface winds are barely a whisper, moving at less than a meter per second. The existence of these layered strata suggests a history that does not match the current reality, implying that the Venus of the past was a radically different world, or that the processes governing the lithosphere today are operating under physics we have yet to fully comprehend. The strangeness permeates the very texture of the ground. In the Venera 13 images, the regolith appears looser, almost soil-like, composed of smaller pebbles and dust. But it is the interaction between the lander and this soil that creates the first sense of unease. When the lander touched down, the impact kicked up a cloud of dust that settled within minutes. In an atmosphere 90 times denser than Earth's, dust should not settle quickly. It should hang suspended, buoyed by the thick, fluid-like air. The rapid settling implies that the particles are not fine dust as we know it, but something heavier, perhaps metallic or cemented clumps of chemical deposition. It suggests that the soil of Venus might be less like sand and more like a heavy, toxic sludge that only mimics the appearance of granular dirt. This material is not just passive debris, it is a chemically reactive blanket that is constantly interacting with the rocks it covers, eating away at them in a process of anhydrous weathering that has no terrestrial equivalent. This sense that the environment is actively hostile, or perhaps even deceptively dynamic, reached a fever pitch in 2012 when Leonid Xan-Formality, a distinguished contributor to the original Venera missions, published a startling analysis of the old data. Reviewing the original telemetry tapes from Venera 13, he claimed to have identified objects that appeared to move, change shape, or disappear over the course of the probe's limited lifespan. He pointed to a disc-shaped object that seemed to change its position, a black flap that appeared in one frame and vanished in the next, and most infamously, a structure he termed the Scorpion. This feature, resembling a segmented arachnid, appeared to emerge from the soil, visible in the images for a short time before vanishing, leaving a groove in the ground behind it. Some formality suggested, controversial as it was, that we might be looking at a form of nitrogen-based life, dependent on the dense hot atmosphere rather than water. The scientific community largely rejected these claims, attributing the movements to noise in the transmission, artifacts of the image processing, or shifting debris caused by the lander's arrival. The Scorpion, many argued, was likely just a piece of the lander itself, perhaps a lens cap or insulation material that had melted and drifted in the heat. However, the psychological impact of the claim remains significant. It highlights the fundamental offness of the images. The Venusian surface is so alien, so distorted by heat haze and optical illusions, that the line between rock, machine, and biology becomes blurred. Whether or not the Scorpion was real is almost beside the point. The fact that the environment creates such convincing simulacra of life is terrifying in its own right. It forces us to confront the possibility that on a world this extreme, the definitions of animate and inanimate might need to be rewritten. The chemistry of Venus is so energetic, so volatile, that non-biological processes could mimic the complexity of life, creating self-organizing structures that grow, move, and decay without ever being alive in the way we understand it. Even if we dismiss the Scorpion as a trick of the light, the rocks themselves harbour a deeper secret. The images show sharp, angular edges on the stones of Venera 14. In a corrosive, high-pressure atmosphere, erosion should be aggressive. Over millions of years, these rocks should have been smoothed down to nubs, polished by the chemical bath they sit in. The sharpness suggests youth. These rocks have not been sitting there for billions of years. They are fresh. This observation aligns with one of the most disturbing theories about Venus, the global resurfacing event. When we map the entire planet using radar, as the Magellan probe did in the 1990s, we find a random distribution of impact craters. On a stable, ancient surface like the Moon or Mars, craters accumulate over time, creating a scarred history where older terrains are more heavily cratered than younger ones. On Venus, the craters are few, and they are spread evenly, as if the entire planet was wiped clean roughly 500 million years ago. This leads to the terrifying conclusion that the surface we see in the Venera images is the aftermath of a planetary cataclysm. The theory suggests that Venus suffers from a cyclic form of plate tectonics, or rather, a lack thereof. On Earth, plate tectonics act as a pressure release valve, constantly recycling the crust and releasing internal heat through volcanic vents and rift valleys. Venus, lacking water to lubricate these plates, has a stagnant lid. The heat from the core builds up, trapped beneath a solid, immovable crust. For hundreds of millions of years, the pressure mounts, the mantle boils, and the planet swells, until finally the crust fails catastrophically. In a geological blink of an eye, the entire surface of the planet melts, sinks, and is overturned, engulfed by a global flood of lava that erases everything. The sharp rocks, the flat plains, the eerie stillness, it is all a temporary facade, a crust hardening over a bomb that is ticking toward its next detonation. The offness we sense in the images is the stillness of a graveyard that has been paved over, waiting for the earth beneath it to heave once more. Above this tortured ground, the atmosphere itself behaves with a manic energy that defies the lethargy of the surface winds. While the air at ground level is a sluggish ocean, the upper atmosphere is a screaming torrent. This is the phenomenon of superrotation. The planet itself rotates with agonizing slowness, taking 243 Earth days to complete a single turn on its axis, longer than its year. Yet the cloud tops whip around the planet in just 4 Earth days, driven by winds reaching 360 kilometers per hour. This disconnect between the planet's rotation and its atmosphere creates a frictional shear that generates immense energy. But the mechanism that sustains this super rotation remains one of the solar system's great unsolved mysteries. by all rights, friction should have slowed the winds down billions of years ago. Something is pumping energy into the system, driving the atmosphere to spin 60 times faster than the ground beneath it. This atmospheric engine manifests in visual anomalies that have been detected not just by probes, but by telescopes on Earth. Observers have long noted the ashen light, a faint ghostly glow on the night side of Venus. First reported in the 17th century, this phenomenon was dismissed as an optical illusion for centuries, much like the canals of Mars. However, modern instrumentation has detected strong pulses of electromagnetic radiation, Whistler waves and optical flashes that suggest the planet is racked by lightning storms of unimaginable intensity. But these are not lightning storms as we know them. On Earth, lightning is generated by water ice crystals colliding in clouds. Venusian clouds are composed of sulfuric acid. The physics of charge separation in such a medium are poorly understood, yet the data is undeniable. The planet is crackling with electrical discharge. The lightning on Venus serves as a beacon, illuminating a cloud layer that harbours the most controversial anomaly of all, the unknown ultraviolet absorber. When we look at Venus in visible light, it appears as a featureless white marble. But when viewed in the ultraviolet spectrum, dark streaks and patches appear, swirling around the planet. These dark patches absorb nearly half of the solar energy the planet receives, playing a crucial role in the thermal balance of the atmosphere. Despite decades of study, we still do not know what chemical substance causes these dark patches. Candidates range from allotropes of sulfur to ferric chloride, but none fit the data perfectly. The absorption profiles change over time, shifting and evolving in a way that some astrobiologists have dared to compare to the blooming of algae in Earth's oceans. This brings us back to the uncomfortable possibility that the something off with Venus is not just geological, but biological. In 2020, the detection of phosphine gas in the cloud decks of Venus sent shockwaves through the scientific community. On Earth, phosphine is produced almost exclusively by anaerobic bacteria or industrial processes. It is a biosignature. To find it in the clouds of Venus, at an altitude where temperatures and pressures are relatively mild, comparable to Earth's surface, suggested that life might be hiding in the acid haze. While subsequent analysis has been fiercely debated, with some attributing the signal to sulfur dioxide or data processing errors, the mystery of the unknown absorber remains. If there is life on Venus, it is not crawling on the hellish surface where the Venera probes landed. It is floating in the sky, riding the super-rotating winds, a biosphere suspended in an eternal acidic storm, utterly disconnected from the dead rock below. The visual evidence from the probes hints at this disconnect. The sky in the Venera images is a uniform, glowing heavy yellow, scattering light so completely that shadows are soft and diffuse. There is no sun, only a pervasive, suffocating luminance. This is the glory of the Venusian greenhouse, a trap that captures solar energy and refuses to let it go. But this light is filtered. The blue end of the spectrum is ruthlessly absorbed, meaning that if you were standing on Venus, you would be colorblind to blue. Everything is rendered in shades of orange, brown, and yellow. This chromatic distortion affects how we interpret the images. The true color of the Venusian rocks is likely a dark grey basalt, similar to the ocean floors of Earth, but under the alien sky, they appear rusty and sickly. We are looking at a world through a lens that fundamentally alters the nature of reality, hiding the true composition of the planet behind a wall of sulfur. Beyond the landing sites of the Venera probes, the radar eyes of the Magellan spacecraft revealed a type of terrain that exists nowhere else in the solar system, a landscape that deepens the mystery of Venus's geological history. These are the tesserae. Named after the Latin word for tiles, these regions are vast, elevated plateaus of intensely deformed crust. They look like a crumpled sheet of paper, folded and faulted in every direction, creating a chaotic jumble of ridges and valleys that defies the logic of standard erosion or tectonic movement. The tesserae are the oldest parts of Venus, the only surviving remnants of the world that existed before the Great Resurfacing event. They are the islands of the past, standing above the frozen lava plains that cover the rest of the planet. The existence of the tesserae suggests that the pre-cataclysm Venus was a very different place. The complexity of the folding implies that the crust was once more pliable, perhaps even thinner, and subject to lateral movements that resemble the plate tectonics of Earth. Some planetary geologists speculate that the tesserae are the cratons of ancient continents, the roots of land masses that might have once been surrounded by oceans of liquid water. If this is true, then the images of the tesserae are the only pictures we have of a lost Earth-like world. They are the ruins of a paradise that was burned away. Looking at the radar maps, one gets the impression of a frantic struggle written in stone, the crust twisting and buckling as the planet died. The visual violence of the tesserae stands in stark contrast to the vast flat plains that surround them. These plains, known as planitia, are unnervingly smooth. In the radar images, they appear dark, indicating a lack of roughness to scatter the signal. This smoothness is the hallmark of fluid lava that settled and froze, burying the original topography under kilometers of molten rock. But even these flat plains are not normal. They are marked by canali, channels that run for thousands of kilometers, longer than the Nile or the Amazon, yet maintaining a consistent width the entire way. These were not carved by water. They were carved by extremely low viscosity lava, possibly carbonatite or sulfur-rich melts, that flowed like river water, cutting deep grooves into the rock before solidifying. The physics required to keep lava liquid for such vast distances is baffling, suggesting an eruption of a scale and duration that is difficult to model. It paints a picture of a planet bleeding out, its lifeblood flowing in rivers of fire that spanned entire hemispheres. Among these plains sit the pancake domes, steep-sided, flat-topped volcanoes that look exactly as their name suggests. They appear to be formed by highly viscous, silica-rich lava that oozed out of a vent and spread evenly in all directions, inflating like a rising dough before solidifying. These domes are often found in clusters, looking like colonies of giant stone organisms. Their presence indicates pockets of evolved magma, different from the basalt of the plains, suggesting a complex internal plumbing system that segregates different chemical mixtures. The diversity of volcanic features on Venus, from the massive shield volcanoes like Mat Mons to the microscopic vents, shows a planet that is trying to turn itself inside out in every way possible. The offness here is the sheer variety of destruction. It is as if the planet is experimenting with every conceivable method of volcanism, a laboratory of geological horrors. The most unsettling feature of the tesserae and the plains is the silence of the data. We see the aftermath of violence, but we see no active change. We have not definitively seen a volcano erupt in real time, though we have strong evidence of recent activity. We see the static corpse of a dynamic process. It creates a cognitive dissonance. The landscape screams of motion, flowing rivers, buckling crust, exploding domes, but the images are frozen. It is like walking into a room where a violent struggle just occurred, the furniture overturned and the glass broken, but the combatants have vanished. We are left to piece together the crime scene, and the suspect is the planet itself. To truly understand the offness captured in the surface images, we must return to the crushing weight of the atmosphere. The pressure at the surface is 92 bars. This is not just a number, it's a physical state that alters the behavior of matter. At this pressure, carbon dioxide is no longer a gas in the traditional sense. It is a supercritical fluid. It possesses the density of a liquid but the viscosity of a gas. This means that the air on Venus is thick enough to push you around like a tide. If you were to stand on the surface, you would not feel a breeze. You would feel a heavy, gelatinous current pressing against you. This supercritical fluid is an incredibly efficient solvent and heat conductor. It wraps around everything, ensuring that the temperature is uniform from the equator to the poles, and from the day side to the night side. There is no escape from the heat. On Earth, night brings relief. On Venus, night is just a darker version of the oven. This fluid atmosphere creates optical distortions that would make navigation impossible for a human explorer. Because the atmosphere is so dense, it bends light severely. This refraction creates a phenomenon where the horizon appears to lift up. If the air were clear enough to see the horizon, which it isn't due to the haze, you would feel as though you were standing in the bottom of a vast bowl. The ground would seem to curve up around you, creating the terrifying illusion that you're trapped in a pit. This fisheye effect is the result of the atmosphere acting like a giant lens, warping the geometry of the world. The images from the Venera landers show a flat horizon only because the view is limited to a few hundred meters. If the camera could see further, the world would distort into a funnel. This geometric nightmare is perhaps the most profound offness of all. the very shape of the planet is perceived differently because the air itself is a magnifying glass. The supercritical CO2 also explains the strange erosion we see, or don't see. While it doesn't rain water, the atmosphere itself scrubs the rocks. The slabs of Venera 14 might be the result of this fluid peeling away layers of rock, like skin, rather than battering them with impact. It is a slow, chemical exfoliation. The planet is dissolving its own surface. This interaction between the supercritical atmosphere and the mineral surface is a realm of chemistry that we cannot replicate easily in labs on Earth. We are looking at minerals that are stable only in hell. If you brought a rock from Venus back to Earth, it might explode or crumble as the pressure releases and the temperature drops, unable to exist in our mild environment. The artifacts of Venus are bound to Venus. The images also reveal a lack of small-scale shadows. On Earth, shadows give texture and depth to the world. They tell us where the light is coming from. On Venus, the light is omnidirectional. The sky is a glowing dome. This flat lighting contributes to the surreal, artificial look of the photographs. It looks like a bad CGI render where the ambient occlusion has been turned up too high. It strips the landscape of drama, leaving only a stark, naked reality. There is no romance in the Venusian landscape, no interplay of light and dark. There is only the relentless, illuminating heat. This lighting condition makes it incredibly difficult to judge distance or scale. A rock could be 10 meters away or 10 kilometers. Without atmospheric reference points like clearer air or distinct shadows, the human eye and the camera lens is lost. The tragedy of these images lies in the comparison. Venus and Earth are twins in size, mass and composition. They formed in the same neighbourhood of the solar nebula, likely out of the same materials. Yet one became a garden, and the other became a gas chamber. The images from the surface are the portrait of the sibling that fell. When we look at the rocks of Venera, we are looking at Earth's potential future. As our sun ages and expands, its luminosity will increase. In 1 billion years, Earth may enter a runaway greenhouse effect similar to Venus. The oceans will boil, the carbonates will bake out of the rocks, and the atmosphere will thicken into a crushing blanket. The offness of Venus is a premonition. It is a ghost of Christmas future. This divergence is what drives the scientific obsession with the planet. How did two worlds, so similar at birth, end up so differently? Was it just a matter of proximity to the Sun? Or was there a specific event, a trigger that sent Venus down the path of ruin? Some theories suggest that Venus once had oceans, perhaps for billions of years. It might have been habitable while Earth was still a molten slag heap. The images of the tesserae and the granite-like compositions detected by recent infrared surveys support this wet Venus hypothesis. If Venus was once wet, then the images we see are not just of a hellscape, but of a ruined civilization. Not of people, but of a biosphere. The something seriously off is the silence of a world that used to sing. The Soviet scientists who processed the Venera images reportedly wept when they saw the first clear pictures. It wasn't just the technical triumph, it was the stark realization of the isolation. The images conveyed a loneliness that is distinct from the desolation of Mars or the Moon. Mars is cold and dead, preserved in a freeze-dried state. The Moon is a vacuum, a void. But Venus is active, angry, and oppressive. The images feel claustrophobic. You can feel the weight of the sky pressing down on the lens. The offness is emotional as much as it is physical. It triggers a primal fear of entrapment. To be on Venus is to be buried alive in the open air. The data transmission itself adds to this eerie narrative. The images were sent back in slivers, line by line, fighting against the static and the dying batteries. The probes were screaming their findings into the void before they melted. The glitches and the noise in the raw images act like scars on the film, reminders of the violence of the transmission. We see the teeth of the data encoding, the jagged edges where the signal dropped out. These artifacts are part of the image now, inseparable from the landscape. They remind us that our view of Venus is stolen, a fleeting glimpse snatched from the jaws of destruction. We were not meant to see this. The planet actively tries to hide its face, crushing anything that gets close, and yet, through the persistence of analog radio and Soviet steel, we peered behind the veil. As we continue to analyze these decades-old images with modern techniques, using AI to sharpen the resolution and remove the noise, we are finding more anomalies. we are finding that the surface is more heterogeneous than we thought. There are patches of different mineralogies, suggesting a complex geological history of differentiation. The boring basalt plains are actually a quilt of different lava flows, separated by millions of years. The planet has a memory. It has recorded its trauma in the layers of rock, and we are just now learning how to read the language of its scars. The offness is simply our inability to read the text. We are trying to interpret a library of books written in fire and pressure, using a dictionary written in water and air. The future of Venus exploration promises to resolve some of these mysteries, but it also threatens to uncover new horrors. Upcoming missions plan to drop probes that will float in the clouds, and landers that can survive for hours or even days. But until then, we are left with the legacy of the Venera program. We are left with those grainy, yellow-tinted windows into hell. They stare back at us, unblinking. They show us a world where the sky is a ceiling of acid, the ground is a hot plate, and the air is a heavy curtain. They show us that the universe is capable of creating environments that are perfectly designed to destroy us. And in the corner of the frame, in the blur of the pixelated soil, the scorpion waits, either a trick of the mind or a sign that life, like the planet itself, can twist into forms we dare not imagine. The offness is not a glitch, the offness is the reality. Venus is the normal, Earth is the anomaly, and the planet is waiting for the anomaly to correct itself.